Before telescopes, before physics, before we even understood what a star was, the sky appeared complete, fixed, contained. The Milky Way looked like the boundary of reality itself, a structure surrounding our world steady and absolute. And in a way that conclusion made sense. Our eyes cannot detect depth in the heavens. We cannot see that some stars are hundreds of times farther than others, or that their light has travelled thousands of years just to reach us. To early observers, everything simply appeared close uniform and self-contained. But this picture was an illusion born from limited tools, a small misunderstanding that would one day collapse in spectacular fashion, because hidden inside that soft glow were clues, subtle differences in brightness, slight shifts in colour, tiny patterns in the positions of stars, signs that the Milky Way was not the universe, but merely one structure inside something far larger. Much larger. What looked like the edge of everything was only the beginning of a much deeper story. A story that would eventually reveal trillions of galaxies scattered across distances so vast that no ancient observer could have imagined them. The universe was never small, only our understanding was. By the early 20th century, astronomy had reached a crossroads. Telescopes were finally powerful enough to reveal strange cloudy objects scattered across the sky, the spiral nebulae. Some astronomers believed these faint spirals were small nearby systems inside the Milky Way. Others argued they might be entire island universes far beyond its boundaries. This disagreement triggered one of the most important scientific disputes in history, the Great Debate of 1920. On one side, Harlow Shapley insisted the Milky Way was enormous and contained everything. On the other, Heber Curtis countered that these spirals were far too structured and too numerous to be local clouds. He suspected they were galaxies in their own right. At the time, no one had the evidence to settle the argument. Photographs were blurry, distances were unknown, and the scale of the universe was still a matter of interpretation rather than measurement. But the spirals refused to fit neatly into the old model. Their shapes, rotations, and brightness patterns didn't behave like nearby gas. They hinted at something bigger, a possibility so uncomfortable that many scientists resisted it. This debate wasn't just about a few faint objects. It was about the size of the universe itself. If Curtis was right, the Milky Way wasn't the entire cosmos. It was just one galaxy among many, maybe millions. A conclusion so radical that accepting it required letting go of everything astronomy had assumed for centuries. What came next would change our understanding forever. For years, astronomers argued about the nature of the spiral nebulae. Were they small clouds inside the Milky Way, or were they something much larger, entire systems far beyond our galaxy? The debate had gone on long enough that both sides started to feel entrenched. It wasn't a theoretical disagreement anymore. It had become a battle over the size of the universe itself, and no one had the evidence needed to end it. That changed the moment Edwin Hubble gained access to the largest and most advanced telescope of his time, the Hooker telescope at Mount Wilson. With this instrument, Hubble could see deeper into the sky than any human in history. And the first target that mattered most was Andromeda, the brightest and most well-known of the spiral nebulae. Andromeda had been photographed many times before, but those images were always soft, featureless blurs. The spirals were visible, some bright knots of light were visible, but individual stars were impossible to isolate. The light blended together, creating ambiguity in every measurement, and ambiguity meant speculation could continue. Hubble's mission was simple. If he could resolve even a single type of star inside Andromeda, whose properties were well understood, he could determine its distance. And from that distance he could settle the debate once and for all. So he focused his attention on variable stars, specifically Cepheid variables. These stars don't shine steadily, they pulse. Their brightness increases and decreases in a predictable cycle, and that cycle reveals their true luminosity. The longer the period, the brighter the star actually is. This relationship, discovered by Henrietta Leavitt, gave astronomers something priceless: a universal measuring stick. Hubble began taking photographic plates night after night, carefully marking which stars changed brightness. It took months of slow, deliberate observation. Cephees do not complete their cycles quickly. Some take days, others weeks. Each plate had to be compared with the one before it, each shift in brightness documented by hand. Then finally he found what he was looking for, a star inside Andromeda, whose brightness varied in a clear, regular pattern. It wasn't a cloud. It wasn't a gas knot. It was a Cepheid, and once Hubble calculated its true luminosity and compared it to how faint it appeared, the answer was inescapable. Andromeda was not within the Milky Way. It was far beyond it, more than 800,000 light-years away. At that time, this distance was enormous. It was far greater than the size of the Milky Way as understood then. A measurement like this didn't just stretch the boundaries of the known universe, it shattered them. If Andromeda was that far away, then it was a galaxy in its own right. A system of stars comparable in size to ours, perhaps even larger. And if Andromeda was a galaxy, then all the other spiral nebulae likely were too. This single discovery transformed our cosmic map in an instant. The universe was no longer a single galaxy with some small clouds around it. It was a universe filled with galaxies, possibly millions of them. Later discoveries would prove it wasn't millions or billions, but trillions. Hubble's work didn't just give astronomers new information, it forced humanity to confront a new reality. The Milky Way is not the universe. It is merely one galaxy in an ocean of galaxies stretching far beyond anything we can ever see with the naked eye. And with that revelation, the scale of existence changed forever. The universe became not just larger than expected, but so large that the human mind struggles to comprehend it. Yet this expansion of understanding didn't stop with Hubble's measurement. It only opened the door to even greater questions. Questions about the origin, structure and fate of this vast collection of galaxies. Hubble had shown us that the night sky was not the boundary of everything. It was only the first layer. When Hubble proved that Andromeda was another galaxy, the universe suddenly became larger. But a bigger universe came with a bigger problem. How do you study something so vast that even light struggles to cross it? How can we measure distances that are far beyond anything we can physically reach? Astronomy, unlike geology or biology, cannot bring samples into a lab. Everything we know must come from one thing: light. Light is the only messenger that travels fast enough and far enough to carry information across the cosmos. But even at its extreme speed, it is still finite. It takes time for light to move, and that time delay becomes the key to understanding the universe. Every time we look outward, we're looking backward, not metaphorically, but literally. A star that sits 100 light-years away sends us light that has been in transit since the early 1920s. We see it as it existed when astronomers were still arguing about spiral nebulae. A galaxy 1,000,000 light-years away shows us what it looked like before humans developed agriculture. A galaxy 1,000,000,000 light-years away shows us a version of the universe that existed long before the Earth formed. There is no way around this. There is no faster route. Every observation is a look into the past. This is the strange paradox of astronomy. Our job is to study the universe, yet we can never observe it as it currently is. We only see snapshots from different eras arranged at different depths on the cosmic timeline. Space is not just a distance map, it is a time map. As telescopes grew more powerful, astronomers quickly realized this wasn't a limitation. It was an advantage. If light preserves the history of the universe, then by looking farther we can effectively peel back the layers of cosmic time. We can reconstruct events that happened billions of years before life on Earth existed. This is why astronomers became obsessed with measuring distance accurately. A star's colour, brightness and spectral lines tell us what it's made of, but without knowing how far away it is, the information is incomplete. Distance transforms raw data into a coherent story. Cepheid variables were the first breakthrough but not the last. Parallax measurements established the nearest stars. Type Ia supernovae extended our reach far beyond Cepheids. Redshift revealed how galaxies move, and that movement could be used to estimate distance on scales far too immense for any other method. Every technique had a range. Every range opened a new layer of the universe. Yet as we built these distance ladders, a deeper realization emerged. Time itself is not evenly distributed across the cosmos. The farther we look, the younger the universe becomes. Galaxies at great distances appear smaller, more chaotic, less structured. Their stars are younger. Their shapes are less stable. Their chemical composition is more primitive. These observations form a consistent picture. The universe has changed dramatically over billions of years. This is where light becomes not just a tool, but a record. Continuous archive stretching from the present day back to near the moment of the Big Bang. When astronomers talk about the early universe, they are not speculating. They have seen it directly captured as faint ancient photons that have been travelling across expanding space for more than 13 billion years. But this also means there are limits. We cannot observe the present-day state of distant galaxies. By the time their light reaches us, they have evolved far beyond the version we see. Some have collided with neighbours. Some have changed shapes entirely. Some no longer exist. Light does not show us the universe as it is. It shows us the universe as it was, and the deeper we look, the further back we go. This understanding fundamentally changed our place in the cosmos. The sky is not a static dome. It is a dynamic timeline filled with objects that are, in truth, all at different ages. Astronomy became a science of history, a discipline where telescopes act as time machines, revealing earlier and earlier chapters of cosmic evolution. Without light's finite speed, we would never have discovered how galaxies form, how stars assemble from cold hydrogen, how cosmic structures emerge from tiny fluctuations in the early universe. We would have no way to confirm the Big Bang, no way to measure cosmic expansion, no way to map our origins. Everything we know about the universe comes from photons that left their sources long ago, each carrying a tiny piece of a much older story. And in the next part of this journey, we will see how those photons revealed something even more surprising. The universe is not just filled with galaxies. It is stretching, changing and expanding on a scale far beyond intuition. Hubble's discovery that Andromeda was a separate galaxy should have been enough to reshape astronomy for a generation, but the real shock came next. When he began measuring the spectra of galaxies far beyond Andromeda, he noticed something peculiar. Their light was stretched, not just faint stretched. The spectral lines were shifted toward the red end of the spectrum, a phenomenon now known as redshift. This wasn't new. Astronomers had seen redshifts before, but they had no clear explanation. Some believed the nebulae might be moving away through static space. Others suspected the shifts were caused by unknown interactions with dust or gas. But when Hubble compared redshift values with the distances, he calculated the pattern was undeniable. The farther a galaxy was, the faster it seemed to be moving away. This wasn't a random scatter of motions. This wasn't orbital drift. It wasn't turbulence or local gravitational chaos. It was a clean linear relationship, a straight line when plotted on a graph. Distance up, redshift up, distance down, redshift down. This observation became what we now call Hubble's law, one of the foundational pillars of modern cosmology, and its implication was more dramatic than any single discovery before it. Space itself was expanding, not galaxies moving through space like debris scattering from an explosion, but space growing between galaxies. The distances increased because the fabric of the universe was stretching. Galaxies were not speeding away. The space between galaxies was becoming larger. This single idea overturned centuries of assumptions. The universe wasn't static. It wasn't eternal in its current form. It wasn't a fixed arena where stars simply lived and died. It was dynamic, a changing structure on the largest possible scale. Einstein himself initially resisted this conclusion. His equations predicted an expanding or contracting universe, but he dismissed those solutions as unrealistic and introduced a cosmological constant to force his model into stillness. After Hubble's findings, Einstein famously remarked that modifying the equations has been his greatest mistake. Once expansion was accepted, everything else in cosmology began to fall into place. It explained why galaxies at vast distances looked younger and more chaotic. It explained why the universe appeared to have a beginning. It implied that if we traced the expansion backward in time, all galaxies, all matter must converge toward a much denser, earlier state. Hubble didn't just prove expansion, he revealed that the universe had an origin. Telescopes became not just tools for seeing farther, but for measuring how the universe evolved over billions of years. Astronomers could estimate the age of the universe from the rate of expansion. They could examine how structures formed and how they changed over time. They could study galaxies as snapshots of different epochs, each giving clues about the universe's youth. But expansion also introduced a new challenge. The farther we look, the faster galaxies recede. And beyond a certain distance, they move away faster than the speed of light. Not because they break physical laws, but because space can expand at any rate. That means there are regions of the universe whose light will never reach us no matter how long we wait. The observable universe became more than a bubble defined by time. It became a bubble defined by both time and expansion. The horizon wasn't just the limit of what we see, it was the limit of what we can ever see. And as the data accumulated, astronomers found something even stranger. Galaxies were not just receding, the rate of their recession was accelerating. Expansion wasn't slowing down under gravity, it was speeding up. Some unknown force, eventually named dark energy, was pushing the universe apart faster and faster. But that is a story for later. In this moment of scientific history, Hubble's work transformed everything. He revealed a universe vastly larger than we imagined. He showed that the cosmos had a beginning, and he provided the first clear evidence that the large-scale structure of reality is in constant motion. The universe is not a silent, static backdrop. It is active, it is growing. It is evolving at a scale that makes human timescales look insignificant. And now that we knew the universe was expanding, the next question was unavoidable. What exactly are we expanding into? That question leads us directly to the next chapter in this journey, the concept of horizons, the true size of the observable universe, and why our view of the cosmos will always be limited. Once astronomers accepted that the universe was expanding, a new realization emerged, one that reshaped our idea of distance, in a way no scientific discovery had done before. If the universe has a finite age and light travels at a finite speed, then there must be a limit to how far we can see. Not because space ends, but because light hasn't had enough time to reach us. This boundary is called the observable universe, and it forms a sphere around us roughly 46 billion light-years in radius. The size is not defined by how far we can build telescopes or how good our instruments become. It is defined by time itself. Light from anything farther than that distance simply hasn't arrived yet and may never arrive. This concept is easy to state but profound in implication. We can only see a tiny fraction of the universe not because our tools are limited, but because reality imposes a hard limit on what information can reach us. The observable universe is often misunderstood. It's not the entire universe, it's just the part whose light has reached our position in space since the Big Bang. Every observer anywhere in the cosmos would see a different observable universe centered on themselves, with different galaxies near the edge. There is no universal center, no privileged vantage point. Every location gets its own sphere of visibility. This revelation forced astronomers to rethink every assumption. When we look deeper into space, we're not just looking farther away, we're looking back in time. Galaxies near the edge of the observable universe appear young, compact, and chaotic, because their light left them more than 13 billion years ago, when the cosmos itself was still in its early stages. The farther out we look, the earlier the universe becomes. Beyond a certain point, we cannot see galaxies at all. Instead, we see only the faint uniform glow of the cosmic microwave background radiation, left over from a time when the universe had cooled enough for atoms to form, about 380,000 years after the Big Bang. This faint pattern is the oldest light the universe has allowed us to observe. Anything before that moment is hidden because earlier the universe was too dense and too hot for light to travel freely. The observable universe is therefore not just a spatial limit, it is a temporal limit. But the structure of this boundary becomes even stranger when we consider expansion. Because space itself is stretching, many regions of the universe are receding from us faster than the speed of light. This isn't a violation of physics, it's simply a consequence of expanding space. Galaxies aren't moving through space faster than light. The space between us and them is increasing. The result is a second, even more restrictive boundary, the cosmic event horizon, the maximum distance from which light emitted right now can ever reach us in the future. It is smaller than the observable universe. This means there are galaxies we can currently see whose ancient light has reached us but whose future light never will. They are effectively lost, receding faster than their photons can travel. We are watching galaxies disappear not due to distance alone but due to the acceleration of cosmic expansion. To visualize this without resorting to metaphors, imagine the universe as a three-dimensional grid where each point drifts away from others as expansion continues. Galaxies aren't racing away. The underlying grid itself is stretching. At small scales between nearby galaxies, gravity keeps everything bound. But farther out, the expansion dominates, and at extreme distances it outruns even the speed of light. This leads to an uncomfortable truth. The observable universe is shrinking in practical terms, not because objects are getting closer, but because expansion is pushing more of them beyond the event horizon. In the far future, galaxies outside our local group will fade from view one by one, red-shifted until they vanish entirely. A distant civilization born tens of billions of years from now would look at the sky and see almost nothing beyond their own merged local galaxies. To them, the universe would appear small, isolated, and static, completely different from the vast interconnected cosmos we see today. We live in a privileged era when enough light has reached us to understand the universe's true scale. But before expansion erases that evidence forever, the horizon of the observable universe is not a wall, but it is a limit. A boundary not of matter but of information. It is the line between what the universe has revealed and what it keeps hidden. And even though we can map what lies within this boundary with increasing precision, the truth remains. Most of the universe will always be beyond our reach, not because we lack technology, but because the structure of space-time itself prevents us from seeing more. In the next part of this journey, we move from what we can see to how all of this is arranged. If the observable universe is the limit of our vision, then the cosmic web is the structure hidden just beneath that vision, a pattern that connects galaxies into something much larger than any one of them. By now, we understand that the observable universe has a limit, a maximum distance from which light has had enough time to reach us. But astronomers soon realize that this is only one of the universe's boundaries. There is another limit layered on top of it, shaped not by the past but by the future. Together, these two horizons determine everything we can ever learn about the cosmos. The first boundary is the particle horizon. This is the edge of the region whose light has reached us since the Big Bang. It marks the farthest point from which information has had enough time to travel to Earth. Nothing beyond this distance is visible to us today. Not because those regions don't exist, but because their light is still on the way, light that may never arrive. But expansion complicates this picture. The universe isn't static, space itself is stretching. And because of this stretching, many regions of the universe move away from us faster than light. This doesn't violate physics, galaxies aren't propelling themselves at impossible speeds. The space between us simply grows at a rate that outpaces the speed of light. This leads us to the second boundary, the event horizon. The event horizon is not about the past but the future. It is the maximum distance from which light emitted right now can ever reach us. Anything beyond this limit is permanently cut off, even if we waited trillions of years, even if we built the most advanced telescopes imaginable, even if our civilization endured longer than stars themselves. Nothing from beyond that event horizon will ever enter our view. This is why astronomers say the universe is divided into two parts. One region whose information can eventually reach us, and another region forever isolated by expansion. The strangest consequence is this: there are galaxies we can see today whose future light will never reach us. Their photons left billions of years ago when those galaxies were much closer, but in the time since expansion has carried them so far away that anything they emit now is effectively lost to us forever. This means the night sky contains objects already gone from our cosmic future. We are seeing them as they were not as they are, and we will never see their later history. The particle horizon tells us what part of the universe's past is visible. The event horizon tells us what part of the universe's future is accessible. These two concepts create a complex, layered structure to our knowledge of the cosmos. Inside both horizons, we can see the past and will continue to receive new information. Inside the particle horizon, but outside the event horizon, we can see ancient light from these regions, but they are already beyond reach. Their future is permanently disconnected from ours. Outside both horizons, we will never know anything about these regions. They are beyond sight and beyond communication. This structure forces us to rethink what it means to see the universe. The observable universe is not just limited, it is asymmetrical. We see deeper into the past than we'll ever see into the future of distant objects. What we observe is not a balanced snapshot. It is a collection of one-way signals, and it will only get more unbalanced with time. As expansion accelerates, the event horizon shrinks relative to the size of the observable universe. More galaxies move beyond contact. Their light fades, stretches, and eventually becomes undetectable. The cosmos doesn't grow quiet all at once. It dims slowly, with one galaxy after another slipping into invisibility as expansion outruns their ability to communicate. This doesn't just affect astronomy, it affects the long-term fate of knowledge. Civilizations born in the far future, tens or hundreds of billions of years from now, may never know that trillions of galaxies once existed. To them, the universe will appear small, empty, and static. They will not see the cosmic web. They will not detect the microwave background. They will not have the clues that led us to the Big Bang. Their universe will seem fundamentally different from ours. Our moment in cosmic time is unique. We live at an era where enough light has arrived for us to reconstruct the universe's history, but before expansion erases that history forever. We're in a narrow window, a brief period where the universe is still legible. Two horizons define that window: the boundary of what we can see from the past, and the boundary of what we can ever see in the future. And together they reveal a sobering truth. The universe is not limited by our instruments. It is limited by the structure of space-time itself. In the next part, we will step beyond these boundaries and look at how matter galaxies and entire clusters assemble into something larger, a structure that spans the observable universe and reveals how the cosmos organizes itself on the grandest scales. Once we understood that the universe is expanding and that horizons limit what we can see, the next question became clear: how is everything arranged within this enormous space? For centuries, astronomers imagined the cosmos as a mostly uniform scatter of stars and galaxies. But as deeper surveys accumulated, a more complex and surprising picture began to emerge, one that challenged our intuition about randomness. In the late 20th century, large-scale galaxy surveys such as CFA-2DF and eventually the Sloan Digital Sky Survey began mapping not just individual galaxies, but the relationships between them. This was the first time humanity attempted to chart the universe in 3 dimensions, covering enormous swathes of space, spanning billions of light years. The results were nothing like what anyone expected. Galaxies were not evenly distributed. They did not form a smooth cloud. Instead, they clustered together on some scales and left enormous empty regions on others. When plotted across vast distances, these galaxy positions revealed a striking structure. an intricate arrangement of filaments, clusters, and voids stretching across the cosmos. This pattern has come to be known as the cosmic web. Filaments' long thread-like structures span hundreds of millions of light-years. At their intersections lie galaxy clusters, some containing thousands of galaxies bound together by gravity. Surrounding these filaments are immense voids, sometimes hundreds of millions of light-years wide, where almost no galaxies exist at all. This was not merely a visual curiosity. It was a fundamental insight into how the universe evolved. Simulations soon showed why this pattern forms. In the early universe, tiny fluctuations in density existed within the nearly uniform sea of matter. Some regions contained slightly more mass than others, differences so small that they were initially almost undetectable. But gravity amplifies these variations over time. Slight overdensities attract more matter. Slight underdensities lose matter to their surroundings. Over billions of years, these tiny fluctuations grow into the massive structures we observe today. The cosmic web is not decorative. It is the natural consequence of gravity acting on matter across cosmic time. Even more striking, these patterns match what cosmologists expect from the influence of dark matter, ordinary matter. The atoms in stars, gas and dust is not enough to create these structures alone. There isn't enough visible mass. Instead, dark matter forms a deeper invisible framework. Ordinary matter collects along these dark matter scaffolds following their gravitational pull. Every filament we observe corresponds to a filament of unseen mass. Every cluster sits in a deep gravitational well sculpted by dark matter. Every void marks a region where dark matter density is low. The cosmic web is therefore both visible and invisible at once, a grand pattern made of galaxies tracing a structure we cannot directly detect. Observations from gravitational lensing confirm this. Light from distant galaxies bends around these giant mass distributions exactly as predicted by dark matter models. The scale of this structure is difficult to comprehend. Filaments can stretch across a significant fraction of the observable universe. Clusters can weigh quadrillions of solar masses, and voids are so large that entire Milky Way-sized galaxies could drift through them without encountering anything for hundreds of millions of years. Yet despite its immense scale, the cosmic web exhibits a surprising level of order. Patterns repeat across vast distances. The same filamentary structures appear in opposite directions of the sky. This uniformity suggests that the universe on its larger scales is governed by simple physical laws, gravity expansion, and the distribution of dark matter applied consistently across space. This revelation carried profound implications. For the first time, astronomers could understand not just the positions of galaxies but the architecture of the universe. They could trace the pathways along which matter flows. They could identify the regions where galaxy formation is most active. They could see how structures evolve over billions of years. And beyond the observational value, the cosmic web shows that the universe is not a random scatter of galaxies. It is a system shaped by predictable forces forming patterns on scales so vast that no single galaxy or even galaxy cluster truly stands alone. Everything is connected through gravity. Everything follows the underlying distribution of matter. Even the largest empty regions exist because of how mass was arranged in the early universe. In this way, the cosmic web is not just a map of where galaxies are. It is a record of the universe's history and a glimpse into its future. In the next part of this journey, we'll go deeper into that unseen component, dark matter, and explore how something we cannot observe directly can shape everything we do see. The discovery of the cosmic web revealed that galaxies do not float randomly through space. They belong to a vast interconnected structure shaped over billions of years. But to truly understand this structure, astronomers needed more than images of galaxy positions. They needed to map the underlying framework that galaxy distribution only hints at, the deeper invisible mass shaping every filament, cluster and void. This hidden architecture is often referred to as the cosmic skeleton. And it is dominated not by stars, not by gas, not even by the galaxies themselves, but by dark matter. Mapping something we cannot directly see may sound impossible. Yet over the past few decades, astronomers have developed sophisticated methods to reconstruct this structure with remarkable precision. These efforts combine three main tools: galaxy surveys, computer simulations, and gravitational lensing. Galaxy surveys provide the first layer. Large projects like the Sloan Digital Sky Survey and the Dark Energy Survey created three-dimensional maps of millions of galaxies. By measuring their positions and redshifts, astronomers can chart the visible part of the cosmic web, the luminous traces that reveal where matter tends to gather. But galaxies only account for a tiny fraction of the total mass. They outline the structure but do not define it. To fill in what galaxies do not show, scientists turn to cosmological simulations. Using supercomputers, researchers input the physical laws that govern the universe, gravity expansion, and the primordial density fluctuations measured in the cosmic microwave background, and let these rules evolve the virtual universe forward in time. The result is a simulated cosmic web that closely matches the observed one, but with far more detail, including the distribution of dark matter. These simulations demonstrate a consistent pattern. Dark matter forms the backbone of the universe. Ordinary matter falls into its gravitational wells, creating galaxies and clusters wherever the dark matter is densest. Voids, on the other hand, form in regions where dark matter is sparse. Without dark matter, galaxies would not assemble into the vast structures we observe today. But simulations alone are not enough. They must be verified against real data. This is where gravitational lensing becomes essential. According to general relativity, mass bends the path of light. The stronger the mass, visible or invisible, the stronger the distortion. By measuring how the shapes of distant galaxies are subtly stretched or twisted as their light travels to us, astronomers can reconstruct the true distribution of mass between these galaxies and Earth. This technique, known as weak lensing, allows scientists to map dark matter directly without relying on its interaction with light. The results are striking. Maps created through lensing align almost perfectly with simulations. Regions predicted to contain large amounts of dark matter show strong lensing signals. Filaments predicted by simulations appear as elongated regions of distorted light. Even the enormous voids, the largest structures in the cosmos, show the expected lack of lensing, confirming their low mass density. For the first time, humanity could create a three-dimensional map of the universe's true mass distribution. These maps reveal that visible galaxies are merely highlights along a much deeper structure. Dark matter dominates the mass budget of the cosmos and shapes its large-scale architecture. The galaxies we see are simply the brightest signposts along this hidden framework. These mapping techniques have also uncovered surprising details. Some filaments connecting clusters are so massive that they form bridges spanning hundreds of millions of light years. Some voids are so large and so empty that they defy intuition. Vast regions containing almost no galaxies and extremely little dark matter. These structures are not anomalies. They are essential features of how the universe evolves. The cosmic skeleton also provides clues about the early universe. Tiny fluctuations in the cosmic microwave background, differences in temperature of just a few millionths of a degree, grew into the massive structures we see today without the gravitational influence of dark matter. These fluctuations would not have produced such large structures in such a short cosmic time. The skeleton we map today is the amplified echo of those ancient imbalances. Mapping this structure reshaped cosmology into a precision science. Instead of guessing the shape of the universe, we now measure it directly. Instead of speculating about unseen mass, we can map it across the sky. Instead of treating dark matter as an abstract concept, we now treat it as a real component with measurable effects on the structure of space. Yet even with these advances, the cosmic skeleton raises new questions. What is dark matter made of? Why does it behave so differently from ordinary matter? And how does this invisible mass interact or refuse to interact with the particles we understand? These questions lead us naturally into the next chapter of this journey, where we explore the elusive nature of dark matter itself, what we know, what we suspect, and why this invisible substance shapes everything we see. As astronomers mapped more of the cosmic skeleton, a new layer of structure emerged, something larger than galaxy clusters, larger even than the massive filaments spanning hundreds of millions of light years. This was the realm of superclusters, the largest gravitationally organized regions in the observable universe. Galaxy clusters, though enormous, are still relatively compact. They hold thousands of galaxies bound together by gravity, but clusters themselves are not isolated. They gather into even bigger arrangements, sprawling structures where clusters line up in extended formations that stretch across unimaginable distances. For decades, scientists assumed these superclusters were simply the next step in the hierarchy, that they were gravitationally bound objects the way clusters were. But the more we measured their motions and distances, the more we realized something unexpected. Many superclusters are not single unified structures. Instead, they are regions where the cosmic web becomes particularly dense, but not necessarily regions where all the matter remains gravitationally connected. This realization forced astronomers to rethink what a supercluster really is. Is it a single object, a collection, a region, or something else entirely? These questions became especially important when we tried to determine where the Milky Way fits into the cosmic landscape. For most of the 20th century, our home was thought to lie in a structure known as the Virgo supercluster, a vast region containing thousands of galaxies, including the Virgo cluster and our local group. But this classification turned out to be incomplete. Virgo was not the full story. It was only a small part of something much larger, something we hadn't yet defined correctly. The breakthrough came when astronomers began studying the peculiar velocities of galaxies, the small deviations in their motion not caused by cosmic expansion, but by gravitational pull from nearby structures. When expansion is subtracted out, a pattern emerges. Galaxies inside a common gravitational basin tend to move in similar directions, falling toward the same attractor. A team led by Brent Tully and Brent Close used this approach to map the flow of galaxies around the Milky Way with unprecedented accuracy. Instead of defining superclusters by shape or density alone, they defined them by dynamics, by how galaxies move in relation to one another. This new method revealed something remarkable. The Milky Way, the local group, the Virgo cluster, and many surrounding clusters all flow toward the same gravitational region. They move together, guided by the deeper structure of the cosmic web. This entire dynamic region is known as Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea spans roughly 520 million light-years, containing around 100,000 galaxies, but what makes it significant is not its size alone. It is significant because it represents the true gravitational basin in which our galaxy resides. Everything inside this basin flows toward a central region known as the Great Attractor, a dense zone buried behind the plane of the Milky Way, difficult to observe directly. The discovery of Laniakea reshaped our cosmic address. We are not simply part of the local group or the Virgo cluster or even the Virgo supercluster. We are part of a much larger dynamic structure whose boundaries are defined not by what we see, but by how galaxies move. This method of mapping superclusters highlights the complexity of cosmic structure. These enormous regions are not rigid objects. They are not islands drifting through space. They are gravitational watersheds, regions where matter flows toward common attractors confined not by physical walls, but by the underlying shape of space-time. Laniakea is only one of many such basins. Neighbouring it is the Perseus-Pisces supercluster, equally vast and influencing galaxies within its own gravitational boundaries. Beyond that lie other enormous structures, some of which form parts of the largest features we've ever detected, such as the Sloan Great Wall and the Hercules Corona Borealis Great Wall. structures spanning billions of light years, though their physical unity is still debated. Yet even these colossal formations fit within the broader pattern set by the cosmic web. They are not exceptions. They are natural consequences of the universe's evolution shaped by initial density variations, dark matter dynamics, and billions of years of gravitational growth. Understanding superclusters and our place within Laniakea forces us to confront a deeper truth. Our galaxy is not central, special, or isolated. It is one participant in an enormous interconnected flow of matter that stretches across hundreds of millions of light years. And this flow is only a small part of the cosmic web, which itself is only a small part of the observable universe. As vast as Laniakea is, it is not the whole universe. It is simply home, a gravitational neighbourhood in a cosmos filled with neighbourhoods just as large, just as complex, and just as dynamic. In the next part of this journey, we'll look beyond what we can see with light and begin examining the invisible component that defines even these enormous structures, the substance that shapes Laniakea, the cosmic web, and nearly all large-scale patterns in the universe. Dark matter. As astronomers mapped the cosmic web and uncovered the vast structure of superclusters, another puzzle began to grow in parallel, a problem that appeared not in the outskirts of the universe, but within individual galaxies themselves. Something was wrong with the way galaxies moved. Their behaviour didn't match the amount of matter we could see, and the more closely we measured them, the more obvious this discrepancy became. This mystery is known today as the missing mass problem. The first major clue that most of the universe's matter is invisible. The issue emerged during observations of galaxy rotation. In a galaxy like the Milky Way, stars orbit the centre, much like planets orbit a star. Inner stars move faster, outer stars move slower. Based on Newtonian gravity, the outer regions should rotate at lower speeds because they feel less gravitational pull from the mass concentrated near the centre. But that's not what astronomers found. In the 1970s, Vera Rubin and Kent Ford made precise measurements of the rotation curves of spiral galaxies. Instead of slowing down with distance, the rotation curves flattened. Stars far from the galactic centre were moving just as fast as those closer in, too fast to be held in orbit by the gravity of visible matter alone. If only the stars, gas and dust we could see were providing the gravity, these fast-moving outer stars should have been flung into intergalactic space. But they weren't. They remained in stable orbits. Something had to be providing additional mass, far more mass than the visible matter accounted for. This wasn't an isolated case. When astronomers examined other galaxies, the same pattern appeared again and again. Flat rotation curves became a universal feature. Whether a galaxy was small, massive, new, or ancient, the outer stars rotated too fast for the visible matter to hold them in place. At first, astronomers questioned their assumptions. Were the observations wrong? Were the instruments miscalibrated? Could Newtonian physics be incomplete on galactic scales? But as measurements improved and new galaxies were studied, it became clear the data were consistent. There wasn't enough visible matter in galaxies to explain their motions. Something unseen was dominating the gravitational landscape. The missing mass did not emit light. It did not absorb light. It did not reflect light. It did not interact with electromagnetic radiation at all. But it exerted gravity, enough gravity to bind galaxies together and shape their rotation curves. This invisible component became known as dark matter. Once astronomers accepted the existence of this unseen mass, they revisited other cosmic structures and the puzzle only deepened. Galaxy clusters, the largest gravitationally bound structures in the universe, also rotated too quickly. Their galaxies moved as though the clusters contained several times more mass than what telescopes revealed. Gravitational lensing confirmed the same conclusion. When light from distant galaxies passed through galaxy clusters, it bent by an amount that could not be explained by the visible mass alone. The bending of light required far more mass again, pointing to a dominant invisible component. Even the cosmic microwave background, the oldest light in the universe, carried imprints of this missing mass. Tiny fluctuations in its temperature pattern revealed how matter was distributed in the early universe. Without dark matter, the universe would not have formed galaxies as quickly as observed. The density fluctuations were too small, and ordinary matter interacted too strongly with radiation to collapse into large structures early on. Taken together, multiple lines of evidence, rotation curves, galaxy clusters, gravitational lensing, and early universe patterns pointed to the same conclusion. Most of the matter in the universe is not made of atoms. It is something else entirely. This missing mass is not a minor correction. It is not a rounding error. Dark matter outweighs ordinary matter by more than a factor of 5. If all visible stars, planets, nebulae, and gas clouds vanished, the universe would lose only a small fraction of its mass. Most of the gravitational structure would remain intact, unchanged, held together by dark matter. The missing mass problem is not simply an observational curiosity. It is the reason galaxies exist as they do. It is the reason clusters form. It is the reason the cosmic web looks the way it does. Without dark matter, the universe would be a very different place, sparse, loosely connected, and far less structured. But identifying the presence of dark matter only raises a deeper question. What is it? It doesn't emit light. It doesn't absorb or reflect light. It doesn't interact with electromagnetic forces. It doesn't collide or clump the way normal matter does. And yet it holds galaxies together. It sculpts the cosmic web. It influences the evolution of the universe on every scale. In the next part of our journey, we will explore what scientists believe dark matter might be, and why. Despite decades of effort, this invisible component remains one of the most elusive mysteries in modern physics. Once the missing mass problem became undeniable, astronomers faced a new reality: the universe. We see the stars, the galaxies, the glowing nebulae represents only a small portion of what truly exists. The rest is dominated by something invisible, something that neither emits nor interacts with light. This component, dark matter, quietly shapes the evolution of the cosmos, forming an underlying framework that everything else follows. But how exactly does something we cannot see shape structures on such enormous scales? To answer that, we must look back to the early universe. Shortly after the Big Bang, matter was distributed almost uniformly, with only tiny variations in density fluctuations, so small they appear as faint temperature differences in the cosmic microwave background. Yet these minuscule variations served as the seeds of all future structure. Ordinary matter made of protons, electrons, and atoms was tightly coupled to radiation during this early era. Light pushed against it, smoothing out density differences and preventing matter from clumping efficiently. But dark matter behaved differently. It did not interact with radiation. It did not feel the pressure of light. It responded only to gravity. While normal matter was held back by radiation pressure, dark matter was free to collapse into gravitational wells formed by the initial density fluctuations. These early dark matter concentrations formed the first halo's dense regions that would later become the centers of galaxies and clusters. As time passed, dark matter halos merged and grew. Small halos joined to form larger ones. These larger halos merged into even more massive structures. Over billions of years, this hierarchical growth produced the enormous gravitational landscape we now observe. Ordinary matter followed this invisible distribution. Gas cooled and accumulated where dark matter was densest. Stars formed inside these gravitational basins. Galaxies assembled within dark matter halos, growing into spirals, ellipticals, and irregular shapes depending on local conditions. Without dark matter, galaxies simply could not form at the speed and scale we observe today. The gravitational pull of ordinary matter is too weak. It interacts too strongly with radiation. It collapses too slowly. Dark matter provided the gravitational boost necessary to assemble complex structures within the age of the universe. But dark matter does more than shape galaxies. It determines the large-scale pattern of the cosmic web. In simulations, dark matter filaments emerge naturally from the evolution of early density variations. Gas flows along these filaments, collecting into knots that become galaxy clusters. The most massive clusters sit at the intersection points of multiple filaments, places where dark matter has formed deep gravitational wells. Gravitational lensing measurements confirm this picture with remarkable precision. Light from distant galaxies bends around these invisible structures exactly as predicted by models. The lensing patterns reveal concentrated masses where no visible matter exists, proving that dark matter defines the deeper architecture of space. The invisible framework extends far beyond individual galaxies. Dark matter halos around galaxies can be hundreds of thousands of light-years wide. Cluster halos extend even farther. Filaments span hundreds of millions of light-years, and the largest structures formed by dark matter influence regions billions of light-years across. Yet despite its enormous influence, dark matter remains elusive. We don't know what particles compose it. We don't know why it interacts so weakly. We don't know why it is 5 times more abundant than ordinary matter. Experiments designed to detect dark matter particles from underground detectors to particle accelerators have not yet found a signal. Decades of searches have narrowed the possibilities, but have not revealed the fundamental nature of this invisible substance. Still, its gravitational effects are undeniable. Dark matter keeps galaxies from flying apart. It shapes the evolution of clusters. It carves out the voids. It sets the stage for cosmic structure at every level. Imagine removing it mathematically, not metaphorically. Simulations without dark matter produce a universe where structure forms too slowly. Galaxies remain small or fail to form at all. Clusters never assemble. The cosmic web becomes weak and muted. The universe as we observe it today would be impossible. Dark matter is not an anomaly. It is the backbone of the universe. Its gravitational influence is the primary force organizing matter on cosmic scales. As our understanding deepened, cosmologists realized that dark matter solves many problems, but leaves one enormous question unanswered. If dark matter explains how the universe holds together, then what explains why the universe is being pushed apart faster and faster? The answer lies in something even stranger, a component of the universe that does not pull, but pushes something that accelerates cosmic expansion itself. In the next part of this journey, we will turn to the force that counteracts gravity on the largest scales. Dark energy, the most dominant yet least understood component of the cosmos. Once astronomers accepted that dark matter must exist, a new challenge came sharply into focus. If this invisible substance shapes the universe, what exactly is it made of? Gravity tells us dark matter exists, but gravity alone cannot identify its fundamental nature. To understand it, physicists needed to go deeper down to the level of particles. The search for the dark matter particle is one of the most ambitious scientific efforts of the modern era. It combines astrophysics, particle physics underground detectors, collider experiments, and cosmological modelling. Each approach attacks the mystery from a different angle. Yet none has yielded a definitive answer. Dark matter remains hidden, even as its gravitational influence defines the structure of the cosmos. The most popular candidate for decades was the WIMP, the weakly interacting massive particle. According to theoretical models, WIMPs would interact through the weak nuclear force and gravity, but not with light. They would be massive enough to provide the gravitational pull needed to form structures in the early universe, and their abundance could naturally arise from high-energy processes shortly after the Big Bang. If WIMPs existed, they would stream through Earth in enormous numbers, billions passing harmlessly through every square centimetre each second. Their interactions with ordinary matter would be extremely rare, but not impossible. A WIMP colliding with an atomic nucleus in a detector could produce a small energy recoil, a detectable signal. This idea drove the construction of large underground detectors, buried deep beneath mountains or inside old mines, shielded from cosmic rays and background radiation. Experiments such as Lux, Xenon, Pandax and others filled massive tanks with liquefied noble gases like xenon or argon. These detectors are designed to be silent, perfectly still environments where even a single unusual particle interaction would stand out. After decades of operation, these experiments have produced some of the most sensitive limits in physics. They have ruled out huge ranges of possible WIMP masses and interaction strengths, and yet no confirmed detection has emerged. Either WIMPs interact far more weakly than expected, or dark matter is something completely different. Another promising candidate is the axion, a hypothetical ultralight particle proposed to solve a problem in quantum chromodynamics. Unlike WIMPs, axions would be incredibly light, so light that vast numbers of them could behave collectively like a field permeating the universe. Axions wouldn't collide with nuclei. Instead, they might subtly convert into photons under the right conditions, allowing experiments like ADMX to listen for faint signals in resonant microwave cavities. The search for axions is still in early stages, but the parameter space is wide and experiments are gradually sweeping through decades of theoretical predictions. If axions exist, they could explain not just dark matter, but also deeper symmetries in the laws of physics. Another possibility is that dark matter may be related to sterile neutrinos, hypothetical particles that mix with normal neutrinos but do not interact through any known force except gravity. These particles would be extremely difficult to detect, but certain small anomalies in X-ray data have fueled speculation about their existence. The Large Hadron Collider has also joined the search. High-energy collisions can create new particles, and detectors look for events where energy seems to vanish, a sign that unseen particles may have escaped. But like underground experiments, collider searches have yet to find convincing evidence. Each experimental failure doesn't narrow the mystery, it widens it. The absence of WIMPs pushes theories toward lighter or heavier candidates, or toward particles that barely interact at all. The absence of axion signals pushes theorists to revisit axion models. Every new constraint eliminates possibilities, but sharpens the remaining ones. At the same time, astrophysical evidence continues to mount. Dark matter behaves like a collisionless fluid in galaxy clusters. It influences rotation curves with consistent precision. It shapes gravitational lensing patterns exactly as predicted. It clumps on large scales but spreads smoothly on small ones. These properties rule out certain particle candidates while supporting others. For example, dark matter cannot be made of ordinary stars, planets, or black holes known as machos, because gravitational lensing surveys have already eliminated most such possibilities. It cannot be warm dark matter with intermediate masses because that would erase small-scale structure. It cannot be purely neutrino-based because that would produce a universe too smooth. The remaining candidates, though numerous, share one thing in common. They must interact extraordinarily weakly with ordinary matter. Dark matter may be a new particle from beyond the standard model. It may be an entire family of particles. It may be something more exotic, a modification of gravity, a hidden sector, or a new field permeating space. But whatever its nature, dark matter is real. Its gravitational effects do not disappear under scrutiny. They strengthen. Every observation of galaxies, clusters, lensing arcs, or early universe patterns confirms its presence with remarkable consistency. The search for the particle continues not because we lack evidence, but because the evidence is overwhelming and incomplete. We have mapped its influence, but not its identity. The deepest question remains, what is the universe made of if not atoms? In the next part of our journey, we turn to the other great unknown, not the substance that holds the universe together, but the force that pushes it apart. Dark energy, the most dominant and mysterious component of the cosmos. For most of cosmic history, astronomers assumed that the expansion of the universe should slow down over time. Gravity, after all, is attractive. Every galaxy is tugging on every other galaxy, pulling inward, working against expansion. Even if the universe continued to expand forever, it seemed obvious that the rate of expansion must gradually decrease. This expectation shaped cosmology for decades until the late 1990s, when two independent teams of astronomers uncovered evidence that overturned this basic assumption and forced the field into a new era of uncertainty. Their tool was a special kind of exploding star known as a Type Ia supernova. These supernovae occur when a white dwarf in a binary system reaches a critical mass and undergoes a runaway thermonuclear explosion. The important point is that they all explode at nearly the same intrinsic brightness. That makes them excellent standard candles useful for measuring distances across billions of light years. By observing how bright these supernovae appear from Earth and comparing that to their known luminosity, astronomers can determine how far away they are. By measuring their redshift, they can also determine how fast their host galaxies are receding. Together, these two pieces of information form a detailed picture of how cosmic expansion has changed over time. What the two teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, discovered was astonishing. Distant supernovae were too faint. Not slightly, not marginally. They were dramatically fainter than expected based on any model of a universe whose expansion was slowing down. The only consistent explanation was that these supernovae were farther away than predicted, which meant the universe had expanded more in the past than expected. This could only mean one thing: the expansion of the universe is accelerating. It was one of the most surprising scientific discoveries of the 20th century. The universe expected to slow down was instead speeding up. Gravity was losing a cosmic tug-of-war it should have been winning. To explain this acceleration, cosmologists introduced a new component: dark energy, a form of energy inherent to space itself. Unlike gravity, which pulls, dark energy pushes. It exerts negative pressure, driving galaxies apart at an increasing rate. It does not dilute as the universe expands. Instead, it remains constant or nearly constant, causing the expansion to accelerate over time. Dark energy now accounts for roughly 70% of the total energy density of the universe. It dominates cosmic dynamics on the larger scales. Every distant galaxy we observe is caught in its influence, carried away faster and faster by the accelerating expansion of space. Yet despite its importance, dark energy remains profoundly mysterious. What is it made of? Why does it exist? Why does it have the particular value we measure? The simplest explanation is Einstein's cosmological constant, the idea that empty space has intrinsic energy. In this model, dark energy is uniform, unchanging, and woven into the very fabric of space-time. But other possibilities remain open. Dark energy might be a dynamic field that evolves over time, similar to the fields found in particle physics. It might interact with other components of the universe in subtle ways. It might even signal the breakdown of general relativity on cosmic scales. Regardless of its nature, the effects of dark energy are unmistakable. Clusters of galaxies that are gravitationally bound will remain together, but anything not bound will drift away. Filaments stretch. Voids grow. Structures on the larger scales become more isolated. The observable universe loses regions over time as accelerating expansion pushes more galaxies beyond the event horizon. In the far future, the cosmos will look very different. Galaxies outside our local group will fade from view. Their light will be redshifted beyond detection. The cosmic microwave background will stretch into wavelengths so long that no conceivable detector could observe it. The universe will appear empty, quiet and cold, not because matter vanished, but because expansion accelerated it out of reach. We live in a rare and temporary era where dark energy exists but has not yet erased the universe's visible structure. This moment allows us to study cosmic evolution, reconstruct the past, and understand the forces shaping everything on the larger scales. The discovery of dark energy did not simply add another component to cosmology. It forced us to rewrite the equations governing the universe's fate. A cosmos once thought to be slowing is instead racing toward an unknowable future. But before we confront that future, we must examine the full composition of the universe as we now understand it, a mixture of ordinary matter, dark matter and dark energy. In the next part, we will explore how these components fit together to form the cosmic energy budget, and why our familiar atoms make up only a tiny fraction of the total. With the discovery of dark energy and the long-established evidence for dark matter, a clearer picture of the universe began to form, one that is profoundly different from the intuitive world built from atoms, light, and familiar physics. When cosmologists tallied the contributions of every known component, the final result was startling. The universe is not dominated by stars or galaxies, or even the matter that forms our own bodies. Instead, most of what exists is invisible. The cosmic energy budget, the breakdown of the universe's total mass energy content, is one of the most significant achievements in modern cosmology. It tells us not simply what the universe contains, but how these components influence its evolution. The smallest fraction, surprisingly, is ordinary matter. All the atoms that make up planets, stars, gas clouds, nebulae, and living organisms amount to only 5% of the universe. This is the matter described by the standard model of particle physics: protons, neutrons, electrons, and the familiar structures that form chemical elements. 5% is enough to produce everything we see from galaxies to life, but it is barely a trace when compared to the universe as a whole. The next component is dark matter, accounting for about 27% of the cosmic budget. Dark matter does not interact with light, but exerts gravitational influence on all scales. It binds galaxies together, shapes their rotation curves, and forms the scaffolding of the cosmic web. Without it, galaxies would disperse and cosmic structure would fail to develop. Yet even dark matter is not the dominant force in the universe. The majority, roughly 68%, is dark energy, a mysterious component driving the accelerated expansion of the universe. Dark energy permeates space uniformly. Its density does not dilute as the universe grows. This makes it fundamentally different from matter. As more space appears through expansion, the amount of dark energy increases proportionally, enabling it to dominate more strongly over time. When combined, these three components form the modern cosmological model known as lambda CDML, representing the cosmological constant dark energy, and CDM standing for cold dark matter. Despite its simplicity, this model fits a vast array of observational data with remarkable precision, but each component behaves very differently. Ordinary matter interacts with light forms, atoms, and builds structure. Dark matter interacts only through gravity shaping cosmic architecture. Dark energy influences the expansion of space itself. The components do not merely coexist, they determine the entire history of the universe. In the early universe, dark matter played a dominant role. Its gravitational pull helped assemble structures before ordinary matter could cool and form atoms. As galaxies grew dark, matter halos provided the environment in which visible structure could emerge. But as the universe expanded and matter became more diffuse, the influence of dark energy increased. Eventually it surpassed matter as the primary driver of cosmic evolution. Today, dark energy dictates the large-scale future of the universe. In the far future, its dominance will grow even stronger. This energy budget is not simply a list of cosmic ingredients. It is a window into the history of cosmic transformation. Each component's influence has risen and fallen over time. Ordinary matter dominated briefly. Dark matter shaped most of cosmic evolution. And now dark energy holds the steering wheel. Yet the most striking fact remains. 95% of the universe is made of components we cannot directly observe. They reveal themselves only through gravity, cosmological measurements, or indirect signatures in the early universe. Even with this knowledge, unanswered questions remain. Why does dark energy have the value it does? Why is dark matter 5 times more abundant than ordinary matter? What happened in the earliest moments of the universe to set these proportions? And most mysteriously, why do these components combine in such a way that sophisticated structures like galaxies and eventually life can form? The cosmic energy budget is a triumph of observational cosmology. but is also a reminder of how much remains hidden. We understand how the universe behaves, but not why these components exist in the first place. To move forward, cosmologists turn to a new approach, using the large-scale structure of the universe to probe its underlying geometry and fate. This leads us to the next part of our journey, the cosmic distance ladder. Baryon acoustic oscillations and the methods used to measure the shape and expansion history of the universe with extreme precision. Understanding what the universe is made of is only part of the story. To understand where the universe is going and where it came from, scientists must determine its shape, geometry, and expansion history. These are not abstract questions. The shape of the universe affects how light travels, how structures form, and how expansion behaves on all scales. If space is curved positively like the surface of a sphere, parallel light paths eventually converge. If space is curved negatively like a saddle, they diverge. If space is flat, they remain parallel. These differences might seem subtle, but they produce measurable effects in the distribution of galaxies, the cosmic microwave background, and the apparent sizes of distant objects. Measuring the shape of the universe requires precise distance measurements, and that is far more challenging than it sounds. Distances in astronomy are not measured with a single method, but with a layered system known as the cosmic distance ladder. The first rung is parallax, the apparent shift of nearby stars as Earth orbits the Sun. This technique provides extremely accurate distances within our galactic neighborhood. The Gaia mission has pushed this method to extraordinary precision, allowing astronomers to calibrate more distant measurements with unprecedented accuracy. The next rung involves standard candles objects whose intrinsic brightness is known. Cepheid variables were the first providing distances to nearby galaxies. Type Ia supernovae extend this to billions of light years. These allow astronomers to trace how expansion changes across cosmic time. But standard candles alone cannot determine the universe's geometry. For that, cosmologists use a second tool, baryon acoustic oscillations, or BAO. BAO are subtle imprints left in the large-scale structure of the universe. In the early universe, pressure waves move through hot plasma, compressing matter at regular intervals. When the universe cooled and atoms formed, these waves froze into place, leaving a characteristic separation scale imprinted in the distribution of galaxies. This scale acts as a standard ruler. By measuring how large it appears at different distances, astronomers can determine how space is stretched over time. BAO provide a geometric check on expansion. If the universe were curved, the apparent size of this ruler would shift in predictable ways. The third method, and one of the most powerful, comes from the cosmic microwave background. The CMB is a snapshot of the universe when it was only 380,000 years old. Tiny fluctuations in its temperature pattern reveal the density composition and geometry of space with extraordinary precision. The angular sizes of these fluctuations tell us how space has expanded since that early epoch. When data from CMB measurements like those from WMAP and Planck BAO surveys and supernova observations are combined, a consistent picture emerges. The universe is very close to flat. Not perfectly flat, tiny deviations may still exist, but flat to within a margin of error smaller than 1%. This means space does not curve back on itself or diverge dramatically. On the larger scales, we can measure Euclidean geometry holds. A flat universe has profound implications. It means the total energy density of the cosmos' ordinary matter, dark matter and dark energy combined, is extremely close to the critical density required to keep cosmic geometry balanced. Too much density would produce a closed universe. Too little would produce an open one. But our universe sits almost exactly on the boundary. Why this is so remains an open question. Some theories invoke inflation, a rapid expansion in the early universe, to explain why space appears flat today. According to these ideas, any initial curvature would have been stretched away, leaving behind a universe that appears flat on observable scales. Still, this explanation raises deeper questions about the underlying physics. Even with flat geometry, measuring expansion remains challenging. Cosmologists must also determine how expansion behaves across time, whether it slows, accelerates, or shifts phases based on the properties of dark energy. This requires comparing distances and redshifts at different points in history. The further back we look, the more the expansion history reveals itself. Bow and supernova data trace this evolution over billions of years, while the CMB provides an anchor at the earliest observable epoch. Together, these methods allow cosmologists to reconstruct a detailed curve describing how the expansion rate changed over time. The result aligns with the lambda CDM model, a universe that decelerated for billions of years under the influence of matter, then began accelerating as dark energy took over. Yet the measurements also reveal subtle tensions, discrepancies between different methods, especially in determining the current expansion rate known as the Hubble constant. Parallax-calibrated supernovae suggest a faster expansion. CMB measurements predict a slower one. This disagreement, known as the Hubble tension, may indicate new physics beyond the standard cosmological model. Are we missing a component in the early universe? Is dark energy evolving? Is our assumption of perfect flatness masking something deeper? Or is there an unknown systematic error in one or more measurements? These questions drive modern cosmology forward. The shape of the universe, once thought to be a settled issue, may hold hidden complexities we have yet to uncover. And while geometry reveals the large-scale structure of space, it also leads to a deeper question. What is the ultimate fate of a universe dominated by dark energy? In the next part of this journey, we explore the cosmic future, the long-term consequences of accelerating expansion, and what awaits the universe in the distant epochs ahead. With the discovery of dark energy and the realization that the universe's accelerating cosmology entered new territory, for the first time astronomers could describe not only the past and present of the cosmos, but also its distant future. In a universe driven by dark energy, expansion does not simply continue, it transforms everything. The acceleration changes the large-scale structure of the cosmos gradually at first, then dramatically over longer timescales. The observable universe is not static. It is shrinking in practical terms as more galaxies cross the event horizon and become permanently unreachable. Every light year added to the expansion carries distant objects farther from us, at increasing speeds, stretching their light to wavelengths that eventually fall outside the range of detection. This process begins subtly. Distant galaxies become redder as their light is stretched. Spectral lines shift further toward the infrared, then the microwave, then beyond. Eventually, many galaxies fade below detectability, as their emitted photons cannot keep pace with the accelerating expansion. Within a few tens of billions of years, only the galaxies gravitationally bound to the Milky Way, namely the local group, will remain visible. Everything else will have crossed our event horizon. The vast cosmic web we observe today, with its filaments and superclusters extending across hundreds of millions of light years, will no longer be accessible. Future astronomers, if they exist, will see a universe that appears small, quiet and static, not because it truly is, but because expansion has removed its distant structure from view. As time progresses, the local group itself evolves. The Milky Way and Andromeda will merge into a single massive galaxy, often referred to as Milkdromeda in scientific literature. This merger is governed not by cosmic expansion, but by local gravity. Dark energy has no effect on gravitationally bound systems at this scale. Stars will continue to orbit. New structures will form. The internal dynamics of the merged galaxy will proceed normally. But beyond this local region, dark energy dominates. Clusters cannot merge across intercluster distances. Filaments thin out. Void regions grow larger. Galaxies isolated by expansion become effectively island universes evolving without external interaction. In the far future, trillions of years from now, the universe enters what cosmologists call the degenerate era, a time when star formation ceases because gas reserves are depleted. Existing stars burn out one by one, transitioning into white dwarfs, neutron stars and black holes. The energy output of galaxies declines, their glow diminishes, the night sky becomes darker, not because space is empty, but because star formation has ended. Dark energy continues to expand space, but its effect becomes less visually dramatic as fewer luminous objects remain. Black holes dominate as the longest-lived structures slowly evaporating through Hawking radiation over incomprehensibly long timescales. 10, 1 till, des, 100 years or more for the largest ones. If dark energy remains constant as predicted by the cosmological constant, the universe expands forever, growing colder and more diffuse. This scenario is known as the heat death, or the big freeze. Particles become separated by distances so vast that interaction becomes impossible. Entropy approaches a maximum. No new structures form. The cosmos evolves toward a state of minimal activity where only the remnants of earlier epochs persist. However, this is not the only theoretical future. If dark energy evolves over time, something still possible in current models, the universe could follow different trajectories. If dark energy slowly diminishes, expansion might continue, but with a different long-term behavior, perhaps stabilizing or transitioning into a new phase. If dark energy strengthens over time, expansion could accelerate so violently that galaxies, stars, planets, and even atoms are torn apart in a scenario called the Big Rip. Observations do not currently support this extreme outcome, but they do not completely rule it out either. Another possibility lies in modified gravity theories suggesting that cosmic acceleration might not come from dark energy, but from a change in the laws of gravity on large scales. If such theories are correct, the future could be more complex than the simple extrapolation of current models. Yet even with these uncertainties, one conclusion remains clear. The universe's long-term evolution is shaped by dark energy far more than by matter. The early cosmos was dominated by radiation. The middle cosmos was governed by matter, but the far future belongs to dark energy. Our era, where galaxies are still visible, where the cosmic microwave background can still be measured, and where structures still interact, is temporary. It is a transitional moment between a dynamic past and a more isolated future. Understanding this future gives cosmologists a deeper perspective on the present. We inhabit a rare time when cosmic signals from billions of light-years away can still reach us. A time when the large-scale structure is still visible. A time before dark energy erases the evidence of cosmic history. In the next part of our journey, we step back from the far future and focus on the present. The complex behavior of galaxies, the forces shaping their evolution, and how these structures reveal the deeper physics operating across cosmic scales. Galaxies are not static islands of stars. They are dynamic systems that grow, collide, transform, and evolve across billions of years. Their histories are written in their shapes, their motions, and the distribution of their stellar populations. To understand how the universe changes over time, we must understand how galaxies behave, because on cosmic scales, galaxies are the primary building blocks of structure. The story begins in the early universe, when dark matter halos provided the gravitational wells in which ordinary matter could accumulate. Gas flowed toward these halos, cooled, and formed the first generations of stars. These early galaxies were small, irregular, and chaotic, reflecting the turbulent conditions of the young cosmos. Over time, galaxies grew through two major processes: accretion of gas and mergers with other galaxies. Gas accretion fuels star formation. When cold gas falls into a galaxy's gravitational well, it settles into a rotating disk and gradually forms new stars. Galaxies with abundant gas continue to generate stars for billions of years, maintaining bright spiral arms and dense star-forming regions. Mergers, on the other hand, are violent. When galaxies collide, their stars rarely hit one another directly. The distances between stars are too large, but their gravitational fields interact strongly. Gas clouds compress, triggering bursts of star formation. Spiral structures warp or disappear. In major mergers, two galaxies can combine to form a larger, more massive system, often transitioning into an elliptical galaxy. These processes explain why galaxy shapes vary. Spiral galaxies typically contain significant amounts of cold gas and active star formation. Their disks remain ordered because they have avoided major disruptive collisions in recent history. Elliptical galaxies, in contrast, often form through mergers. Their stars follow random orbits rather than organized rotation. They are dominated by older stellar populations and have little cold gas left to form new stars. Galaxy evolution is also shaped by environment. Dense regions of the cosmic web, such as clusters, host frequent interactions. Galaxies there experience tidal forces, ram pressure stripping from hot intra-cluster gas, and gravitational encounters with neighbors. These mechanisms can remove gas-suppressed star formation and transform spirals into ellipticals. In quieter regions far from massive clusters, galaxies evolve more gradually. They draw in fresh gas from surrounding filaments, replenish their star-forming reservoirs, and maintain their disks for billions of years. Another key influence on galaxy evolution is feedback, the energy returned to the interstellar medium by stars and black holes. Massive stars explode as supernovae, heating and dispersing the gas around them. Supermassive black holes found in the centers of nearly all galaxies can drive powerful jets or outflows that affect star formation on galactic scales. These feedback processes regulate how quickly galaxies form stars. Without them, gas would cool too efficiently, producing more stars than observed. With them, galactic ecosystems become self-regulating. Star formation accelerates when gas supply increases and slows when feedback heats or ejects gas. Observations from space telescopes reveal this cycle in detail. Young galaxies contain dense clusters of massive blue stars, bright, short-lived and explosive. As galaxies age, these populations fade, replaced by long-lived red stars. Ellipticals shaped by past mergers contain almost exclusively old stars, while spirals display a mixture of populations across different regions. The chemical composition of stars also records galactic history. The first stars formed from hydrogen and helium produced in the Big Bang. Later generations contain heavier elements forged in earlier stars. By analyzing stellar metallicity, astronomers can reconstruct when galaxies formed, how often they merged, and how vigorously they produced stars. Large surveys such as those conducted by the Hubble Space Telescope and more recently the James Webb Space Telescope reveal the full progression from small irregular galaxies in the early universe to mature spirals and massive ellipticals today. JWST in particular has shown that galaxies formed earlier and more rapidly than previously believed, challenging long-standing models of star formation and growth. Despite this complexity, galaxy evolution follows clear patterns. Large galaxies tend to grow earlier and then quench, shutting down star formation. Smaller galaxies evolve more slowly, continuing to form stars across cosmic time. Interactions shape morphology, while dark matter defines the gravitational environment in which evolution unfolds. The future evolution of galaxies is equally clear. In our own cosmic neighborhood, the Milky Way and Andromeda are on a collision course that will reshape both galaxies. After they merge, star formation will eventually decline as gas supply diminishes. Over trillions of years, stellar remnants will dominate the merged system, but in the wider universe, interactions will become rarer. As expansion accelerates, galaxies drift apart faster than gravity can pull them together. The rich tapestry of galactic encounters we see today is temporary. The universe's distant epochs will be populated by isolated galaxies evolving internally, cut off from external influences. Galaxies reveal the universe's changing conditions. They show us how matter organizes itself. They record the interplay between gravity, gas radiation, and dark matter, and they provide the clearest window into the processes that shape cosmic structure over billions of years. In the next part of this journey, we will examine one of the most dramatic drivers of galactic evolution, the role of supermassive black holes, and the extraordinary influence they exert on their host galaxies. At the heart of nearly every massive galaxy lurks a supermassive black hole, an object millions to billions of times. The mass of the Sun compacted into a region smaller than our solar system. These black holes are not passive byproducts of galactic evolution. They are active participants shaping their host galaxies in profound ways. For much of the 20th century, astronomers believed supermassive black holes were rare, found only in the brightest active galactic nuclei. But improved observations revealed a different story. The Milky Way hosts a 4 million solar mass black hole known as Sagittarius Ege. The Andromeda Galaxy contains a black hole more than 100 million solar masses. Elliptical galaxies contain black holes hundreds of millions to billions of solar masses. This ubiquity raised a fundamental question. How do black holes and galaxies grow together? The first clue came from an unexpected correlation. When astronomers measured black hole masses across different galaxies and compared them with the galaxy's bulge masses or stellar velocity dispersions, they found a remarkably tight relationship. Larger galaxies host more massive black holes in precise proportion. This correlation, known as the M-sigma relation, suggests that black hole growth and galaxy evolution are linked through a common physical mechanism. It is unlikely to be accidental. Something must regulate both black hole and galaxy growth, keeping them in balance. To understand this connection, we must explore how supermassive black holes interact with their surroundings. Contrary to the popular image of black holes as endlessly devouring everything nearby, these objects spend much of their time quiet. A black hole grows only when gas or stars fall toward it. But when gas does approach, the energy released in the process can be enormous. As matter spirals inward, it forms an accretion disk that heats to extreme temperatures. The disk emits intense radiation across the electromagnetic spectrum. In some cases, magnetic fields channel energy into powerful jets that shoot out from the poles of the black hole at near-light speeds. These outbursts, whether radiative, mechanical, or both, inject tremendous energy into the surrounding galaxy, influencing gas dynamics on scales far larger than the black hole itself. This is known as AGN feedback, active galactic nucleus feedback, and it plays a central role in regulating star formation. In galaxies with abundant cold gas, black holes can flare into active phases, heating or expelling that gas. This prevents the gas from collapsing to form new stars, effectively quenching star formation. In massive clusters, black hole jets carve cavities in the hot intracluster medium, preventing runaway cooling flows that would otherwise form vast numbers of stars. Without this feedback, simulations predict galaxies would grow far too large and form stars at rates much higher than those observed. The universe would look dramatically different. Supermassive black holes enforce a kind of equilibrium limiting how fast galaxies can grow. But the relationship is not one-sided. Black holes also depend on galaxy evolution for their fuel. Major mergers, for example, drive gas toward galactic centers, triggering starbursts and feeding black holes. The largest black holes, those with billions of solar masses, likely grew during periods of intense merger activity in the early universe. The discovery of extremely massive black holes in very young galaxies observed by the James Webb Space Telescope raises new questions. How did these black holes grow so large so quickly? Traditional models struggle to explain their rapid formation. New theories propose direct collapse black holes, dense primordial clouds, or enhanced accretion efficiency. These early black holes may have acted as anchors around which the first massive galaxies assembled. Supermassive black holes also impact galaxies on long timescales. Their gravitational influence extends deep into galactic centers, shaping stellar orbits. In some cases, binary black holes formed from galaxy mergers may produce gravitational wave signals detectable by future observatories. Even after black holes stop growing, their past activity leaves signatures in the distribution of gas and stars. Despite their central role, many aspects of supermassive black holes remain unknown. How do seed black holes form in the early universe? What determines whether a black hole enters an active phase or remains dormant? How do black holes influence galaxy morphology and long-term evolution? What physical limits govern their growth? Each question ties directly back to galaxy evolution and cosmic structure formation. Supermassive black holes are not isolated anomalies. They are engines that regulate the flow of matter energy and momentum on galactic scales. They shape the growth of stellar populations. They sculpt the distribution of gas. They define the internal dynamics of galaxies and leave behind lasting imprints. In many ways, galaxies are ecosystems and supermassive black holes are their central regulators. In the next part of our journey, we shift from galactic centers to the environments between galaxies, the vast intergalactic medium, and the role it plays in fueling galaxies forming structures and recording the thermal history of the universe. Between galaxies lies a vast environment that is neither empty nor static. This region, known as the intergalactic medium IgM, fills the space between galaxies with diffuse matter, thin gas, ionized particles and traces of heavier elements carried across cosmic distances. Though it is incredibly sparse compared to the interiors of galaxies, the IgM contains most of the ordinary matter in the universe. It forms the backdrop against which galaxies evolve. To understand the structure of the universe, we must understand the IgM. It is the channel through which matter flows into galaxies. It is the reservoir feeding star formation. It is the archive holding records of cosmic heating and ionization. The IgM began its story shortly after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen. The cosmos entered a period known as the Cosmic Dark Ages. Without stars or galaxies, the universe was mostly dark. Light could not travel far because neutral hydrogen absorbed ultraviolet photons efficiently. This changed when the first stars and galaxies formed. Their intense radiation began to ionize the surrounding hydrogen, gradually transforming the IgM into a hot ionized plasma. This era, called cosmic reionization, unfolded over hundreds of millions of years. As more stars and galaxies ignited, ionized bubbles expanded and merged, eventually reionizing the entire universe. The IgM we observe today is largely a product of this reionization. It is hot ionized and structured by the gravitational influence of dark matter and galaxies. Its temperature varies depending on proximity to galaxies' quasars and large-scale structures. Because the IgM is so diffuse, it does not emit light directly, but it reveals its presence in other ways. One of the most important methods for studying the IgM involves observing the light from distant quasars, brilliant supermassive black holes actively accreting matter. As this light travels through the universe, it passes through clouds of hydrogen in the IgM. Each cloud absorbs light at a specific wavelength, leaving characteristic dips in the quasar's spectrum. This absorption pattern is known as the Lyman alpha forest. Each line in the forest corresponds to a pocket of hydrogen along the line of sight. Together, these lines form a detailed map of the IgM structure, density and temperature across billions of light years. The Lyman alpha forest reveals that the IgM traces the cosmic web. Dense regions along filaments show stronger absorption. Voids show weaker absorption. The pattern aligns with simulations of dark matter distribution, confirming that the IgM sits atop the universe's hidden scaffolding. Galaxy formation is intimately connected to the IgM. Galaxies grow by drawing gas from their surroundings, pulling it along filaments. This fresh cold gas fuels star formation. Without it, galaxies would quickly exhaust their internal reservoirs and fade. At the same time, galaxies return energy and material to the IgM. Supernova explosions expel heavy elements, carbon, oxygen, silicon into intergalactic space. AGN outflows and jets heat the IgM, altering its temperature and ionization state. These processes enrich the IgM with the chemical signatures of stellar evolution. Even isolated galaxies influence the IgM. Their ultraviolet radiation helps maintain the ionized state of hydrogen across cosmic distances. In this way, the IgM and the galaxies it surrounds form a symbiotic system. Galaxies shape the IgM and the IgM sustains galaxies. The temperature of the IgM also narrates the thermal history of the universe. After ionization, the IgM cooled slowly as the universe expanded. Later, the rise of quasars reheated it through intense ultraviolet radiation. Today, the temperature of the IgM varies widely from tens of thousands to millions of degrees Kelvin depending on location. A significant portion of the IgM exists in a state known as the warm-hot intergalactic medium WHIM, with temperatures between 100,000 and 10 million degrees. This WHIM likely contains much of the missing baryonic matter that escaped earlier observations. X-ray and ultraviolet measurements increasingly support the idea that the WHIM is the primary reservoir of ordinary matter outside galaxies. Despite its low density, the IgM plays a crucial role in shaping cosmic evolution. It influences the growth of galaxies, the formation of clusters, and the behavior of gas across the cosmic web. It preserves the imprints of early heating events and records the influence of black holes, quasars, and stellar feedback. In the far future, as galaxies exhaust their gas supplies and star formation winds down, the IgM will become increasingly quiet. The exchange of material between galaxies and the IgM will slow, and the universe will transition to a more passive state dominated by isolated structures. But for now, the IgM remains the connective tissue of the cosmic web, a dynamic evolving environment that bridges galaxies and reveals the physics underlying the largest structures in the universe. In the next part of our journey, we explore the region where cosmic history is most clearly preserved. Galaxy clusters, the largest gravitationally bound structures in the universe, and the laboratories where matter, gas, dark matter, and black hole activity collide on colossal scales. Galaxy clusters represent the most massive gravitationally bound structures in the universe. While galaxies are impressive on their own, clusters dwarf them. A single cluster can contain thousands of galaxies, vast amounts of dark matter, and enormous reservoirs of superheated gas. These structures sit at the intersection points of the cosmic web, where matter has accumulated over billions of years. Clusters form through hierarchical growth. Small groups of galaxies merge into larger groups. These groups merge into clusters. Along the way, dark matter halos combine, creating deeper and deeper gravitational wells that draw in material from surrounding regions. Because of this hierarchical process, clusters provide a unique glimpse into the universe's formation history. The largest clusters, such as the Coma cluster, the Perseus cluster, and the Virgo cluster, weigh more than 1,000,000,000 times the mass of the Sun, yet only a small portion of this mass comes from stars. Most of a cluster's baryonic matter exists not in galaxies, but in the intracluster medium. A vast diffuse cloud of gas heated to tens of millions of degrees. This gas emits X-rays, allowing telescopes like Chandra and XMM Newton to map its structure. These X-ray observations reveal shocks, turbulence, and cavities carved out by energetic processes, particularly those driven by supermassive black holes at the centers of large galaxies. The intracluster medium is so hot that atoms are fully ionized, and collisions between particles create a complex plasma environment that records a cluster's violent past. But the largest contribution to a cluster's mass comes from dark matter. Gravitational lensing measurements show that dark matter forms the primary backbone of every cluster, making up around 85% of the total mass. By observing how clusters bend the light from background galaxies, astronomers can map this unseen matter with remarkable accuracy. These lensing maps often show substructures, remnants of past mergers, unresolved halos, and features that reveal how clusters assembled over time. One of the clearest demonstrations of dark matter's existence comes from galaxy clusters, the famous Bullet cluster. A collision between two massive clusters provides striking evidence. When the clusters collided their gas clouds, the baryonic material interacted, slowed down, and produced bright X-ray emissions. But gravitational lensing revealed that most of the mass passed through unimpeded, separating from the gas. This mass corresponds to dark matter, which does not collide or interact the way gas does. The Bullet cluster shows that dark matter behaves as a collisionless substance consistent with cosmological models. Cluster galaxies also offer insights into how galaxies evolve in dense environments. In clusters, interactions are frequent. Galaxies experience tidal forces, high-speed encounters, and the removal of gas through ram pressure stripping as they move through the intracluster medium. These processes can suppress star formation, turning once active spiral galaxies into quiescent ellipticals. Clusters are therefore laboratories for studying environmental effects on galaxies. Star formation rates decline. Gas reserves diminish. Morphology transforms over time. The cluster environment accelerates galactic aging, producing populations dominated by old red stars. At the centers of clusters lie massive galaxies known as CD galaxies. These giants often result from repeated mergers and contain some of the largest known supermassive black holes. Their influence extends far beyond their immediate surroundings. Jets from the central black hole can carve cavities in the intracluster medium, displacing gas and injecting energy on scales spanning tens or hundreds of thousands of light years. Clusters also contain evidence of cosmic history in their hot gas, the abundance of heavier elements. Oxygen silicon iron tells astronomers how many generations of stars contributed material to the cluster. The temperature distribution reveals past shocks, collisions, and active periods of black hole feedback. These signatures provide a timeline of cluster formation and evolution. Beyond individual clusters lie even larger structures called superclusters and filamentary complexes. But unlike clusters, these enormous regions are not gravitationally bound as single objects. They expand with the universe and their components move apart over time. Galaxy clusters, in contrast, are stable structures resistant to cosmic expansion because their internal gravity dominates. In the distant future, as dark energy continues accelerating expansion, galaxy clusters will become even more isolated. Material from surrounding filaments will fall in more slowly. Eventually the inflow will halt. Clusters will remain as islands of matter drifting apart from one another. Some astronomers predict that clusters could become the final habitats of matter in the deep future. As galaxies within clusters merge, star formation dies out and black holes grow. Clusters may evolve into massive dark structures dominated by stellar remnants and long-lived black holes. Galaxy clusters hold answers to many cosmological questions. They reveal the distribution of dark matter. They show how gas behaves under extreme conditions. They demonstrate the influence of black hole feedback, and they trace the growth of cosmic structure from early times to the present. In the next part of our journey, we step beyond clusters and look at the largest coherent structures ever observed: giant cosmic walls, filaments and superclusters that stretch across billions of light years and test the limits of our cosmological models. By the time astronomers mapped galaxy clusters with precision, a new set of discoveries pushed the boundaries of cosmic structure even further. Clusters are the largest gravitationally bound systems, but they are not the largest arrangements of matter. Beyond them lie vast formations, immense walls, sheets, and filaments stretching across distances so great they challenge our understanding of how structure forms in a universe governed by dark matter expansion and the physics of the early cosmos. These structures are not bound like galaxy clusters. They expand with the universe and are shaped by the underlying distribution of dark matter. They represent coherence on a scale measured not in millions but in billions of light years. One of the first hints of these megastructures came from the CFA redshift survey in the 1980s. Astronomers expected galaxies to be more or less evenly distributed on the larger scales. Instead, they found immense formations like the Great Wall, a sheet-like arrangement of galaxies stretching hundreds of millions of light years in length. This was the first clear evidence that the cosmic web contains features far larger than clusters and groups. Later surveys uncovered structures even more impressive. The Sloan Great Wall, identified in 2003, stretches over 1 billion light years. The Hercules Corona Borealis Great Wall, reported in 2013, may span more than 10 billion light years. although its physical coherence remains debated. Other candidates, such as the Boss Great Wall and large quasar groups, show similar scales. These discoveries sparked intense debate. According to the cosmological principle, a foundational assumption of modern cosmology, the universe should appear uniform and isotropic on sufficiently large scales. This means that beyond a certain size, structures should blend into statistical smoothness, but walls spanning billions of light years seem to push against that assumption. Do these large structures violate cosmology's underlying principles, or are they statistical outliers formed within the limits of current models? Simulations suggest that structures approaching 1 billion light-years are plausible within the lambda-CDM framework. However, structures significantly larger raise questions about whether they represent genuine physical formations or are artifacts of observational selection, alignment, or data interpretation. Some may be chance associations of smaller structures aligned along our line of sight. Others may be interconnected regions of the cosmic web rather than single continuous objects. Despite these uncertainties, the existence of enormous coherent patterns is undeniable. They form along the densest regions of dark matter filaments, where gravitational evolution has stretched and amplified initial density fluctuations from the early universe. The physics behind their formation lies in the same processes that shape the cosmic web: gravity amplifying small perturbations, dark matter guiding the flow of baryonic matter, and expansion stretching structures over billions of years. These megastructures also provide valuable cosmological tests. By measuring how their distribution compares with predictions from simulations, astronomers can evaluate whether the lambda-CDM model holds on the larger scales. They also use these structures to probe baryon acoustic oscillations, relics of sound waves imprinted in the early universe, which act as standard rulers for measuring cosmic expansion. The larger structures often serve as anchor points in these analyses, helping refine measurements of the universe's geometry, expansion rate, and matter content. Their statistical distribution reveals whether the universe truly becomes homogeneous on large scales, or whether deviations exist that might signal new physics. Another fascinating aspect of these large formations involves the large-scale flow of galaxies. Some regions of space exhibit coherent motion toward massive attractors like the Shapley supercluster, one of the most massive nearby concentrations of galaxies. Observations of galaxy velocities reveal that even enormous regions are influenced by deeper gravitational topology, hinting that the cosmic web's largest features still reflect the early universe's initial density field. Yet even as we study these vast structures, we must recognize their temporary nature. Dark energy is accelerating cosmic expansion, gradually stretching these giant formations. In the far future, the connections between clusters within these walls will weaken. Filaments will become thinner as material flows toward local gravitational centers. Superclusters will fragment into isolated clusters that drift apart indefinitely. What we see today, the grand interconnected cosmic web, represents a specific moment in the universe's evolution. The larger structure appear coherent because we observe them before accelerated expansion has fully separated their components. They are temporary snapshots of a young universe still connected by gravity on massive scales. In the distant future, these structures will no longer exist in any meaningful way. Their galaxies will recede beyond one another's horizons, leaving behind isolated regions of matter surrounded by vast voids. The cosmic web will fade not because it collapses, but because expansion erases its connections. Understanding the largest cosmic structures is not just an exercise in scale. It is a glimpse into the universe's past and future. They reveal how small fluctuations grew into enormous patterns. They show how dark matter and baryons cooperate to form structure. They test our cosmological assumptions at the boundaries of observable reality. These vast formations mark the culmination of structure formation in our accelerating universe. Beyond this scale, gravity cannot organize matter any further. Cosmic expansion dominates, and the universe enters an era where large-scale growth has effectively ceased. In the next part of our journey, we shift from the architecture of the cosmos to the question that surrounds everything. How did all of this begin? To answer it, we must explore the earliest moments of the universe, the realm of the Big Bang cosmic inflation, and the physics that set the initial conditions for everything we observe today. To understand why the universe looks the way it does today with galaxies, clusters, and the vast cosmic web, we must trace its story back to a time before any structure existed. Long before stars ignited, before atoms formed, before light could even travel freely, the universe was a dense, hot, rapidly changing environment governed by extreme physics. These earliest moments set the initial conditions that shaped everything that followed. The journey begins not at the formation of galaxies, but at a point where the laws of nature as we know them were only beginning to operate. Modern cosmology describes the Big Bang not as an explosion in space, but as the expansion of space itself from an extremely hot, dense state. At the earliest measurable times, fractions of a second after the beginning, the universe was a seething mixture of particles and radiation, at temperatures so high that no stable structures existed. During the first tiny fraction of a second, the universe may have undergone a dramatic phase known as cosmic inflation. According to this idea, space expanded exponentially, growing far faster than the speed of light, an expansion allowed by general relativity, because it is space itself that stretches. Inflation solves several problems in cosmology. It explains why the universe appears so uniform on large scales, why its geometry is so close to flat, and why tiny quantum-level fluctuations grew into the seeds of future structure. These fluctuations are crucial. During inflation, microscopic variations in density were stretched across vast cosmic distances. When inflation ended, these variations remained imprinted in the energy distribution of the universe. Over billions of years, gravity would amplify them. Regions slightly denser than average would attract more matter, eventually forming galaxies and clusters. Regions slightly less dense would become the cosmic voids we observe today. In this way, the earliest quantum fluctuations became the blueprint for the entire cosmic web. After inflation ended, the universe continued to expand and cool. Within the first second, protons and neutrons formed. After a few minutes, these particles fused into the lightest atomic nuclei, hydrogen, helium, and traces of lithium in a process known as primordial nucleosynthesis. This set the chemical foundation for the entire cosmic future. Heavier elements would not appear until much later, forged inside stars. For hundreds of thousands of years, the universe remained a dense plasma of charged particles and photons. Light could not travel far because it scattered off free electrons. This era is often described as opaque, not because darkness prevailed, but because photons could not move freely enough to carry information across large distances. About 380,000 years after the beginning, the universe cooled enough for electrons to combine with nuclei. This milestone, called recombination, produced neutral atoms for the first time. As electrons settled into stable orbits, photons were suddenly free to travel. The universe became transparent. The first light capable of crossing cosmic distances was released, the light we now observe as the cosmic microwave background. This ancient radiation provides a direct image of the universe at that early moment. Its faint temperature variations map the initial density fluctuations that inflation produced. These patterns are the earliest observational evidence of structure formation. For nearly 100 million years after recombination, the universe entered a quiet period often called the Cosmic Dark Ages. There were no stars yet, no galaxies, and no sources of visible light. Hydrogen and helium gas filled space uniformly, slowly responding to gravitational attraction. The dark matter halos formed during earlier phases deepened, drawing gas into their centers. This gradual collapse began the transition from a smooth universe to a clumpy one. Eventually, gravity concentrated enough gas inside these halos to ignite the first stars. These stars were massive, hot, and short-lived. Their ultraviolet radiation began to ionize the surrounding hydrogen, ending the Dark Ages and marking the beginning of the first era of illumination. As more stars formed, the process accelerated. Small proto-galaxies merged, growing into larger systems. Supermassive black holes emerged, forming the first quasars. All of this sprang from those earliest fluctuations set in motion before structure existed. These initial moments explain several features of the modern universe: why galaxies form where they do, why the cosmic web has its filamentary shape, why dark matter and ordinary matter clump together, and why large-scale structure looks statistically similar in every direction. The earliest universe established the rules. Everything since has been the unfolding of those initial conditions under gravity expansion and the physics of matter. In the next part of our journey, we explore the rise of the first stars, how the universe transitioned from darkness to light, and how those primordial stars reshaped everything that followed. After the universe became transparent at recombination, it entered a period of profound silence. No stars burned, no galaxies shone. The only light came from the fading glow of the early universe, steadily cooling, steadily stretching as space expanded. This was the era known as the Cosmic Dark Ages. During this time, the universe consisted almost entirely of neutral hydrogen and helium formed during primordial nucleosynthesis. These atoms slowly accumulated in the densest regions of dark matter halos. Gravity began to shape the first structures, but the process was slow. Hydrogen and helium radiate very inefficiently, which means gas could not cool quickly. Without cooling, gas resists collapse. Without collapse, stars cannot form. Nevertheless, gravity continued its patient work. Slightly denser regions attracted more matter. Small dark matter halos gained mass and grew deeper, pulling in more gas from their surroundings. Over tens of millions of years, the most massive halos reached the threshold where gas could finally collapse enough to ignite nuclear fusion. This transition, the birth of the first stars, ended the cosmic dark ages and transformed the universe forever. These first stars, known as population 3 stars, were unlike any stars that exist today. Because the early universe contained no heavy elements, the gas was chemically pristine. Heavy elements, carbon, oxygen, silicon, iron, had not yet been forged. Without these elements to aid cooling, the gas collapsed into much larger clumps than modern star-forming clouds. As a result, population 3 stars were extraordinarily massive. Many are believed to have had masses tens or even hundreds of times greater than the Sun. Some may have exceeded several hundred solar masses. These giants were extremely hot, shining with intense ultraviolet radiation. They burned their fuel rapidly, living short and violent lives that ended in either supernova explosions or direct collapse into black holes. Their existence was brief in cosmic terms. Some lived only a few million years, but their influence was immense. First, their ultraviolet light began reionizing the universe. Neutral hydrogen absorbs ultraviolet light efficiently, so the radiation from population 3 stars ionized the hydrogen around them, creating expanding bubbles of ionized gas. As more stars formed, these bubbles grew and merged. Over several 100 million years, the universe transitioned from a neutral state back to an ionized one, a milestone known as the Epoch of Reionization. Second, these stars produced the first heavy elements. In their cores, they fused hydrogen and helium into progressively heavier nuclei. When the most massive stars exploded as supernovae, they expelled these newly forged elements into surrounding space. This enrichment fundamentally changed the chemistry of the universe. For the first time, gas clouds contained the raw materials needed to form planets, complex molecules, and long-lived stars like the Sun. Third, some population 3 stars collapsed directly into black holes, possibly forming the initial seed. Black holes that would later grow into supermassive black holes found in modern galaxies. This connection may help explain why the James Webb Space Telescope has discovered massive black holes at surprisingly early times, only a few 100 million years after the Big Bang. As the first stars enriched the universe and altered its ionization, state conditions changed rapidly. Gas cooling became more efficient. Star formation spread into newly enriched regions. Small protogalaxies merged into larger ones, forming the earliest recognizable galactic structures. The once uniform cosmic environment evolved into a diverse and complex landscape of halos, filaments, and early galaxies. The end of the Dark Ages was not a single moment, but a gradual transformation. Different regions reionized at different times depending on local star formation rates. Quasars powered by growing black holes added to the ionizing radiation, accelerating the process. Eventually, the universe became mostly transparent to ultraviolet light once again. Observations from modern telescopes provide glimpses of this transition. The cosmic microwave background shows how neutral hydrogen reionized across cosmic time. Deep infrared observations reveal early galaxies on the edge of visibility. Absorption patterns in quasar spectra track the gradual disappearance of neutral hydrogen in the intergalactic medium. These data pieces form a coherent picture of the universe's first great transformation, from a dark neutral environment to one illuminated by the first stars and structured by the first galaxies. Without population 3 stars, the universe would lack the heavy elements required for rocky planets, complex chemistry, or life. They ignited the cosmic dawn and set the stage for everything that followed, from the formation of galaxies to the emergence of solar systems like our own. In the next part of this journey, we explore how those early galaxies assembled, how they grew from small protogalactic fragments into the massive spirals and ellipticals we observe today, and how the universe transitioned from primordial simplicity to the rich cosmic landscape we know. Once the first stars ignited and began transforming their surroundings, the universe entered a new period of rapid change. The light and energy released by population 3 stars altered the chemistry of the cosmos, carved ionized regions into the neutral intergalactic medium, and enriched nearby gas with heavier elements. But perhaps their most important legacy was that they enabled the birth of the first galaxies. Before recognizable galaxies existed, the universe hosted countless small dark matter, halos, gravitational wells drawing in gas from the expanding cosmic environment. These early halos varied in size, with the smallest containing just enough mass to allow molecular hydrogen cooling. Within these halos, star formation began in scattered pockets, producing clusters of massive population 3 stars. These stellar groups were the earliest building blocks of galactic structures. As more halos accumulated mass, they grew deep enough for atomic cooling to occur, allowing gas to collapse more efficiently. This triggered a new wave of star formation. Over time, halos merged, combining their gas stars and dark matter into larger systems. These mergers were messy, turbulent, and frequent. The earliest galaxies were irregular and clumpy, shaped by collisions rather than by stable rotational dynamics. Deep observations from space telescopes reveal evidence of these early systems. They appear compact, bright in ultraviolet light, and dominated by star-forming regions. Their irregular shapes reflect the chaotic environment of the young universe, where gravitational interactions were intense and structures were still assembling. The first galaxies were small compared to modern ones. Many may have contained only a few million to a few 100 million stars, yet their impact was disproportionate. Their intense radiation accelerated reionization. Their supernova explosions enriched gas across large volumes. Their gravitational interactions seeded larger structures that would develop over billions of years. As time passed, these primitive galaxies began to grow through a combination of processes. The first was continuous gas accretion. Filaments of the cosmic web funneled fresh cold gas into galactic halos. This gas settled into rotating structures that gradually developed into early disks. Star formation increased. Stellar feedback reshaped the internal dynamics. The second major process was hierarchical merging. Smaller galaxies collided and combined into larger ones. In each merger, stars from both systems were redistributed into new configurations. Gas clouds collided and compressed, igniting new bursts of star formation. The remnants of these mergers sometimes form the cores of future massive galaxies. Over hundreds of millions of years, galaxies transitioned from chaotic clumps to more coherent structures. The earliest large galaxies displayed intense star formation rates, producing stars far more rapidly than typical galaxies today. Many were likely responsible for a significant portion of the ultraviolet radiation driving reionization. The formation of supermassive black holes also influenced early galactic growth. As seed black holes accreted matter and merged during galactic interactions, they began producing energetic outflows that regulated star formation. Although their effect was smaller than in later epochs, these early black holes contributed to shaping the balance between gas cooling and heating. The James Webb Space Telescope has provided a remarkable window into this period. Its infrared sensitivity allows astronomers to identify galaxies existing only a few 100 million years after the beginning of the universe. These observations show that galaxies formed earlier and grew faster than many theoretical models predicted. Some of the earliest galaxies appear surprisingly massive and well-organized, raising questions about the efficiency of star formation and the behavior of dark matter in the early cosmic environment. The emergence of ordered galactic structures marks the end of the most turbulent phase of cosmic evolution. As galaxies continued to grow, they eventually developed recognizable morphologies: disks, bulges, and extended halos of stars. Interactions remained common, but as the universe expanded, collisions gradually became less frequent. By 1 billion years after the beginning, the cosmic landscape had changed dramatically. The Dark Ages were long gone. The intergalactic medium was mostly ionized, and galaxies had begun forming the first large-scale structures that would evolve into modern clusters and filaments. The rise of the first galaxies set the stage for everything that followed. The growth of massive spirals, the formation of enormous ellipticals, the emergence of galactic clusters, and the assembly of the cosmic web. These early systems were small in size, but they unlocked the mechanisms that would define cosmic evolution for billions of years. Their stars enriched the universe. Their gas flows shaped future generations of stellar birth. Their mergers built the frameworks of modern galaxies. In the next part of this journey, we explore how galaxies transitioned from these primitive structures into the mature systems we observe today, including the origins of rotational disks, the formation of galactic bulges, and the long evolutionary path that led to galaxies like the Milky Way. By the time the universe reached its first billion years, the earliest galaxies had already begun assembling into more complex systems. These protogalaxies were still small and irregular, shaped by repeated mergers and intense episodes of star formation. But as cosmic expansion gradually reduced interaction rates, their chaotic growth transitioned into a more orderly phase. This shift allowed the emergence of one of the most recognizable galactic structures, the spiral galaxy. Understanding how spirals form requires examining several interconnected processes: the cooling of gas, the dynamics of angular momentum, the influence of dark matter, halos, and the long-term behavior of gravitational instabilities within galactic disks. In the early universe, galaxies accumulated gas primarily through inflow along cosmic filaments. This gas carried angular momentum, which determined how it would move once inside a galactic halo. When the inflowing gas reached the inner regions, it began to settle into a flattened structure. Collisions between gas clouds dissipated energy without removing angular momentum, causing the gas to form a rotating disk. This was the essential first step in spiral formation. Star formation inside this disk proceeded rapidly. Dense regions collapsed to form new stars, while supernova explosions injected energy back into the gas, maintaining a dynamic environment. Over time, the interplay between cooling star formation and feedback created a self-regulated system where gas continuously cycled between cold reservoirs and hot pressurized regions. Dark matter halos played a stabilizing role. Their large extended mass distributions shaped the gravitational environment, allowing disks to maintain coherence even as they grew. Without the support of dark matter, disks would be far more fragile and easily disrupted by minor interactions. As the disk became more massive, it developed density waves regions where matter temporarily concentrated as it orbited the galactic center. These waves did not rotate at the same speed as individual stars or gas. Instead, they moved as long-lived patterns, creating the spiral arms we observe today. These arms are not rigid structures. They are zones of enhanced density where gas clouds are compressed, triggering new star formation. Bright young stars illuminate the arms, making them visible across vast distances. The emergence of a central bulge is another key step in galactic maturation. Bulges can form through two primary pathways: mergers and internal evolution. Early mergers often built the foundational bulges of massive spirals. Later internal processes, such as the gradual movement of stars from the disk toward the center, contributed additional structure. The balance between these mechanisms determines whether a spiral galaxy develops a large classical bulge or a small disk-like pseudo-bulge. Over billions of years, interactions with smaller galaxies also shaped the outer regions of spirals. When dwarf galaxies were absorbed, their stars often settled into extended halos rather than joining the disk. These halos preserve clues about a galaxy's accretion history. Streams of stars, tidal remnants, and faint outer structures record past mergers that occurred long after the early chaotic era had ended. The transformation from a protogalaxy to a mature spiral was not uniform across the universe. Larger galaxies formed disks earlier, while smaller galaxies continued experiencing frequent interactions that prevented stable disk formation. Gas availability also played a major role. In regions where the intergalactic medium remained rich in cold, gas spirals could continue building massive star-forming disks. In denser environments where gas stripping was common, many galaxies evolved instead into ellipticals. Simulations of galaxy formation highlight how sensitive disk development is to the balance between gas cooling and feedback. Too much cooling leads to unstable, overly compact disks. Too much feedback disrupts disk formation altogether. The fact that real spirals exist in such large numbers suggests that galaxy evolution followed finely tuned conditions over cosmic time. As disks grew and evolved, they gradually developed additional structures such as bars, elongated regions of stars extending from the galactic center. Bars act as engines of internal evolution, funneling gas toward the central regions and triggering star formation, or feeding central black holes. Many spirals host long-lived bars that reshape their internal dynamics. By around 5 billion years after the beginning, spiral galaxies had become common across the cosmos. Their star formation rates were high, their disks well established, and their structures recognizable. The Milky Way likely reached this mature state during this period, forming a stable disk with well-defined spiral arms and a growing central bulge. The transition from irregular protogalaxies to mature spirals marks a major turning point in cosmic history. It represents the shift from chaotic assembly to organized evolution, from rapid merging to gradual internal development. The galaxies familiar to us today are products of this long transformation, yet the story does not end with spirals. Over time, star formation slows, gas supplies diminish, and interactions reshape morphology. Some spirals retain their structures for billions of years. Others evolve into lenticular or elliptical systems as their disks fade or are disrupted. In the next part of our journey, we examine how mature spirals like the Milky Way age, how their star formation changes over time, and how internal and external processes gradually transform their structures as the universe continues to evolve. Once spiral galaxies reached maturity with well-formed disks, stable rotation, and organized patterns of star formation, their evolution slowed. The universe was no longer the chaotic environment of earlier epochs. Mergers became less frequent. Gas accretion continued, but at reduced rates. The behavior of spiral galaxies entered a long gradual phase in which internal processes began to dominate their evolution. A mature spiral galaxy balances several physical mechanisms. Its rotation stabilizes the disk. Its gas supply fuels star formation. Its stars age and migrate through different orbital paths. Its central black hole shapes the surrounding region through intermittent activity. Together, these factors determine how a spiral galaxy ages. One of the key features of this phase is the gradual decline in star formation. Early in cosmic history, spirals formed stars at high rates because cold gas was abundant and continuously fed by the surrounding intergalactic medium. Over time, however, this inflow weakened. The gas reservoirs inside galaxies were consumed by ongoing star formation and expelled through stellar feedback. As a result, many spirals experienced a slow but steady decrease in star formation activity. The Milky Way provides an example of this long-term trend. It formed most of its stars billions of years ago. Today, its star formation rate is modest compared to its peak. Other spirals show similar patterns. Their brightest, bluest regions gradually fade as young stars diminish, leaving behind a population increasingly dominated by older, redder stars. Internal dynamics also shape the evolution of mature spirals. Bars form and dissolve. Spiral arms shift in strength and pattern. Stars migrate outward or inward due to resonances within the disk. These processes do not drastically alter the galaxy's morphology, but they subtly rearrange its stellar populations over billions of years. The disk thickens as stars age and gradually heat kinematically. The central bulge grows slowly as stars drift inward, or as gas funnels toward the nucleus and forms new stellar populations. Gas depletion is equally important. Spiral galaxies rely on cold gas to sustain star formation. When gas becomes scarce, star formation slows regardless of how stable the disk remains. Several mechanisms contribute to gas loss. Gradual consumption by star formation. Heating by supernova feedback. Gentle outflows driven by stellar winds. Environmental stripping in denser regions. In isolated regions, spirals can maintain moderate star formation for long periods. But in groups or clusters, interactions with the intracluster medium can strip gas from their outer regions. This process, called ram pressure stripping, leads many spirals to lose the fuel needed to sustain their disks. Over time, their star-forming regions retreat inward, and their outer disks fade. Minor mergers also play a role in shaping mature spirals. While major mergers can destroy disks, minor mergers, the absorption of small satellite galaxies, occur frequently without catastrophic disruption. These interactions can thicken the disk, build the stellar halo, and introduce fresh gas that temporarily boosts star formation. The Milky Way has absorbed many such satellites, and evidence of these interactions remains visible in tidal streams and halo structures. The evolution of mature spirals is not solely driven by internal dynamics and gas physics. The central supermassive black hole continues to influence its surroundings. Although its accretion rate is typically low during this phase, occasional activity can heat or disturb gas in the inner regions. These episodes do not drastically reshape the galaxy, but they contribute to the overall regulation of star formation. As the universe ages and gas supply dwindles further, spirals face a gradual transformation. Some will retain their disks for billions of years, slowly fading but maintaining their morphology. Others, especially those in denser environments, will lose their gas more quickly and transition into lenticular galaxy systems with disk-like shapes but little star formation. Still others may eventually experience mergers that transform them into ellipticals. The long-term fate of a spiral depends on its surroundings, its gas content, and its merger history. In low-density environments, spirals can survive for extremely long periods. In high-density regions, their transformation occurs much earlier. As spirals age, their stellar populations grow older. Their disks become less luminous, and their spiral arms weaken. Yet their basic structure remains intact and less perturbed by external forces. The universe still contains many mature spirals even billions of years after their formation. This slow evolution marks a contrast with the rapid assembly of the early cosmos. It reflects a universe entering a calmer, more stable era, one in which the major structures are already in place and internal processes take precedence. In the next part of our journey, we explore how spirals eventually transition into elliptical or lenticular galaxies. We examine the interactions, environments, and internal mechanisms that drive these profound morphological changes across cosmic time. As the universe aged and interactions between galaxies became less common, the pathways driving large-scale morphological transformation also evolved. Mature spirals could remain stable for billions of years, but they were not immune to change. Under the right conditions, especially in crowded environments, spirals could evolve into lenticular or elliptical galaxies. This transformation reflects the cumulative effects of mergers, gas depletion, and environmental processes acting over cosmic time. One of the most significant drivers of this evolution is the merger history of a galaxy. Major mergers, collisions between galaxies of comparable mass, had the power to reshape galactic structure completely. When two spirals collided, their ordered rotation was disrupted. Gas clouds collided and compressed, triggering intense bursts of star formation. Stars were thrown into random elliptical orbits, erasing the organized structure of the disks. After the encounter settled, the remnant often resembled a massive rounded system dominated by older stars. An elliptical galaxy. These mergers were more common in the early universe when galaxies were closer and interactions more frequent. As cosmic expansion reduced the average density of galaxies over time, major mergers became rarer. However, in dense regions such as galaxy clusters, interactions remained frequent enough to continue driving the formation of elliptical galaxies well into later epochs. Not every galaxy followed the pathway of a major merger. Minor mergers, the absorption of smaller satellite galaxies, also played a role. In spirals, repeated minor mergers gradually thickened the disk and contributed to the growth of the bulge. If this process continued long enough, the disk's ordered structure could weaken. Combined with slow gas loss, this could produce a transformation into a lenticular galaxy, a disk-like object with little or no star formation, lacking the clear spiral patterns of its earlier state. Environmental factors further accelerated these transformations. In dense clusters, the intracluster medium exerted strong pressure on galaxies moving through it. This pressure stripping removed gas from spiral galaxies, especially from their outer regions. Without gas, star formation declined and spiral arms faded. Over time, the galaxy transitioned into a lenticular system. This pathway required no mergers. It was driven entirely by environmental conditions. Gravitational interactions also played a role. Close encounters between galaxies could disturb their disks, heat their stellar populations, and induce tidal forces that altered their shapes. Repeated encounters gradually eroded the orderly structure of spirals. In extreme cases, these interactions triggered internal instabilities that reshaped the disk from within. Supermassive black hole activity contributed as well. When galaxies merged, their central black holes often merged too, releasing enormous energy into the surrounding medium. This energy could heat or expel gas, preventing further star formation. In some cases, black hole feedback alone was enough to quench a galaxy's star-forming activity, nudging it toward a transition. The formation of elliptical galaxies reflects these combined processes. Ellipticals are characterized by random stellar motions, large bulges, and smooth light profiles. They contain old stellar populations, very little cold gas, and almost no current star formation. Their existence demonstrates that evolution can erase the dynamic, rotating structures of spirals and replace them with systems dominated by the remnants of long-past interactions. Lenticular galaxies occupy an intermediate space. They retain a disk-like shape but lack active star-forming regions. Their stellar populations are older, their gas reservoirs depleted, and their spiral patterns absent. Lenticulars may form through quiet gas depletion or through more disruptive processes. Their diverse origins make them valuable markers of environmental influence. The relative abundance of spirals, lenticulars, and ellipticals changes across different environments. Spirals dominate low-density regions where interactions are infrequent and gas accretion can continue for longer periods. Lenticulars and ellipticals are common in clusters where environmental stripping merger activity and gravitational interactions reshape galaxies efficiently. Simulations support this picture. They show spirals forming early, growing through gas inflow and eventually transitioning to quiescent systems as gas supply diminishes. Major mergers produce ellipticals, while minor mergers and environmental processes produce lenticulars. The details vary, but the overall evolutionary pathways are consistent. Observational evidence reinforces these models. Deep surveys reveal early spirals merging into massive ellipticals during the universe's first few billion years. Cluster studies show spirals losing gas as they fall inward, transitioning into lenticulars. Galactic fossils such as stellar streams and outer halos record past interactions that shape the current morphology. The transformation from spirals to ellipticals illustrates the gradual shift in cosmic evolution. In the early universe, structures assembled rapidly. In the middle epochs, spirals matured and evolved internally. In later epochs, the lack of available gas and the dominance of environmental shaping led to the rise of quenched systems. But these pathways are not just historical, they foreshadow the future. As gas continues to diminish across the universe and star formation slows, more spirals will transition into quiescent forms. Some will merge, others will fade quietly. The diversity of galactic structures observed today is a snapshot of a transitional cosmic era, one in which spirals remain common, but are slowly giving way to more passive systems. In the next part of our journey, we explore the ultimate fate of galaxies in an accelerating universe, how spirals, ellipticals, and lenticulars evolve under the influence of dark energy, and what the far future of cosmic structure will look like as expansion accelerates and gas supplies vanish. As the universe continues to expand under the influence of dark energy, the long-term future of galaxies becomes increasingly dominated by isolation, dwindling resources, and the gradual decline of star formation. The organized structures that define spirals, ellipticals, and lenticulars today will not remain unchanged. They will evolve in response to both internal processes and the accelerating expansion of space. The first major change concerns the loss of cosmic connectivity. In the present universe, galaxies are still linked by filaments of gas and dark matter that guide the inflow of material. These large-scale structures allow galaxies to grow through accretion and occasional mergers, but as expansion accelerates, the distances between galaxy groups increase faster than gravity can pull them together. The cosmic web begins to thin, filaments stretch, gas inflow slows. Over immense timescales, galaxies lose access to external reservoirs of matter. In this accelerating universe, only galaxies bound together by gravity remain connected. The Milky Way and Andromeda, along with several dozen dwarf galaxies, form such a bound structure. Over the next few billion years, these systems will merge into a single massive galaxy. The same pattern occurs elsewhere. Galaxy groups collapse internally while becoming more isolated from the rest of the universe. Beyond these bound groups, more distant galaxies gradually fade from view as their light becomes stretched to longer wavelengths. Eventually, they cross the cosmic event horizon, a boundary beyond which light emitted today will never reach us. In practical terms, the observable universe shrinks. Future inhabitants of these merged galaxies would see a much emptier cosmos, unaware that countless galaxies once existed beyond their isolated island of matter. The second major change concerns the decline of star formation. Even in the absence of accelerated expansion, galaxies face a finite supply of cold gas. Star formation consumes this gas over time. Feedback from stars and supermassive black holes heats or ejects part of it. Without replenishment from the intergalactic medium, galaxies gradually exhaust their fuel. Spiral galaxies will be among the first to experience this decline. Their star formation depends heavily on cold gas in their disks. When this gas is depleted, their spiral arms fade and their disks become dominated by older stars. Over billions of years, a once vibrant spiral transitions into a passive dimmer system with limited capacity for new stars. Lenticular galaxies represent an intermediate stage of this transformation, already lacking the gas needed to sustain star formation. Elliptical galaxies which exhausted their gas long ago change little in appearance. Their stellar populations age, their light reddens. Over extremely long timescales, their evolution becomes dominated by internal stellar processes rather than by external influences. As galaxies age, their internal structures also shift. Bars may weaken as disks fade. Bulges become more prominent relative to diminishing disks. Stellar halos grow more diffuse as dynamic processes redistribute stars. Galaxies also continue to merge internally. Within gravitationally bound groups, smaller galaxies spiral inward through dynamical friction and merge with the dominant central galaxy. This process increases the mass of central black holes and contributes new stellar populations to the remnant. But without external galaxies available as merger candidates, this internal evolution eventually slows as well. Far in the future, galaxies experience changes on even longer timescales. Star formation ceases entirely. White dwarfs cool into black dwarfs. Neutron stars drift in slowly decaying orbits. Planetary systems become unstable as passing stars alter their trajectories. The galaxy becomes a quiet collection of stellar remnants orbiting within a dark matter halo that has stopped growing. In this distant epoch, occasional collisions between stellar remnants may still occur, forming new black holes. But these events become increasingly rare. Most of the galaxy's mass resides in long-lived star stellar remnants, and the central supermassive black hole which continues to grow slowly by capturing stray objects. Meanwhile, dark energy pushes unbound galaxies beyond each other's horizons. Clusters become isolated islands drifting apart in ever-expanding space. The large-scale cosmic structures that define the present universe gradually lose their coherence. Filaments fade, voids grow, superclusters fragment. This future is not violent but gradual. It unfolds over billions, trillions, and eventually quadrillions of years. The universe transitions from a dynamic interconnected environment to a patchwork of isolated galaxies that can no longer influence one another. The ultimate fate of these galaxies and of all cosmic structures depends on the long-term behavior of dark energy. If dark energy remains constant, expansion continues forever, and galaxies drift increasingly out of contact. If dark energy evolves, more exotic scenarios could unfold. Current evidence supports a steady acceleration, suggesting a future in which galaxies become the last coherent structures in a vast expanding space. The universe of the far future is shaped less by growth and more by decline, less by interaction and more by isolation. Galaxies become monuments to a time when cosmic structure formation was active. They persist, but without the ability to create new stars or to gather new material. In the final part of our journey, we examine the ultimate fate of the cosmos itself, the deep future in which even galaxies, black holes and particles encounter the consequences of an eternally expanding universe. As galaxy groups merge and the accelerating expansion of the universe isolates them from the rest of the cosmos, the final era of structure formation begins. No new galaxies will form from cosmic filaments. No new inflows will replenish gas reservoirs. The universe enters a slow transition from activity to quiet endurance, shaped by the diminishing resources of time and energy. The first major change is the end of star formation. Even in the most resilient galaxies, cold gas becomes increasingly scarce. Without fresh gas, molecular clouds cannot collapse, and the birth of new stars grinds to a halt. Blue short-lived stars vanish first as their final generations exhaust their fuel. Galaxies lose their vibrant regions of ultraviolet light and become dominated by long-lived dimmer red stars. Over trillions of years, the universe becomes a landscape of aging stellar populations. Red dwarfs, the longest-lived stars, persist the longest. Their lifetimes stretch from tens to hundreds of trillions of years. They shine faintly but steadily, slowly consuming hydrogen with unmatched efficiency. Eventually, even these last stars reach the end of their lives. They cool into dark remnants, leaving behind no source of new light. As star formation ends, the internal dynamics of galaxies continue to evolve. Stellar remnants gradually settle into long-term orbits. Some systems become unstable as interactions between passing remnants alter trajectories. Planetary systems drift into new configurations. Over extreme timescales, gravitational encounters eject planets into intergalactic space, or send them spiraling into their host remnants. The central supermassive black holes remain. These black holes grow as they capture stray stars, black dwarfs, or compact objects. In isolated future galaxies, the central black hole may eventually become the most massive single object left. But even this process slows over time as available material decreases. Long after the last stars have faded, a new era begins, the era of black dwarfs, neutron stars, and black holes. White dwarfs cool into black dwarfs, dark objects radiating only the faintest heat. Neutron stars remain stable, slowly drifting through the galaxy. Black holes persist, warping the space around them. The universe continues expanding, and the cosmic microwave background, once brilliant then faint, stretches into wavelengths so long it becomes undetectable by any conceivable technology. The cosmos grows darker, colder, and more diffuse. As expansion accelerates, distances between isolated galaxy remnants increase exponentially. Even within gravitationally bound groups, motion slow. Mergers become rare. The universe transitions from dynamic motion to relative stillness, a quiet persistence of long-lived structures enduring across unimaginable time. Eventually, the dominant process becomes the evaporation of black holes. According to theoretical predictions, black holes emit radiation due to quantum effects at their horizons. For large black holes, this emission is extraordinarily faint. They take time periods far longer than the current age of the universe to evaporate, timescales measured in unimaginable orders of magnitude. Yet given enough time, even the largest black holes lose mass and ultimately disappear, releasing their remaining energy into the cold, expanding universe. After the final black hole evaporates, the universe enters its last known phase. No stars remain to shine. No galaxies remain in recognizable form. No black holes persist to anchor gravitational systems. All that is left is a sparse distribution of particles, protons, electrons, neutrinos, and the faint radiation left from the evaporation of black holes. At this stage, the universe approaches what physicists call thermal equilibrium. There are no significant sources of free energy. No gradients remain to drive complex processes. The cosmos has expanded so far and cooled so thoroughly that physical change becomes extraordinarily limited. This outcome is sometimes described as the heat death of the universe. Not a violent end, but a gradual fading of all structure, all light and all motion toward a uniform cold state. The universe does not collapse or explode. It simply runs out of the ability to create organized complexity. Yet even in this distant future, the universe retains a kind of record. The distribution of particles reflects the structures that once existed. The leftover radiation reflects events from across cosmic history, and the very expansion of space bears the imprint of the earliest moments of the cosmos. From its beginning as a hot, dense environment filled with potential to its middle age, filled with galaxies and stars, to its distant future, shaped by expansion and decay, the universe tells a coherent story. Each phase emerges naturally from the one before it. Each structure, from subatomic particles to galaxy clusters, arises from the same physical laws acting over different scales and different eras. As our journey through the cosmos reaches its conclusion, we stand in a rare moment, a moment when galaxies are still visible, when the cosmic microwave background can still be measured, and when the large-scale structure of the universe remains intact. Future observers separated by trillions of years would not see what we see. They would live in an isolated galaxy unaware of the rich cosmic landscape that once filled the universe. We occupy a privileged vantage point in cosmic time. It is temporary, it is unique, and it allows us to understand the grand narrative of the universe before its structures fade into the deep future. This final part closes the long arc of cosmic history from the earliest quantum fluctuations to the last remnants of structure. It is the story of everything the universe built, everything it transformed, and everything it will eventually relinquish.